It's fun.
Okay, so I hear that the keynote is about to start. So let's switch over to that.
Please join me in welcoming Chad Arimira to the stage.
Hello, and welcome to JavaOne 2025. Thank you, thank you. If this is your first JavaOne, raise your hand. Wow. All right, everyone whose hands are not up, I want you to introduce yourself at the end of the keynote to one of those people. Originally built for set-top boxes, 30 years ago, the Oak programming language evolved into what we know as Java today. It launched with the vision of being simple, object-oriented, distributed, productive, secure, and highly performant. These things may seem obvious today, even a bunch of buzzwords, but 30 years ago, they were revolutionary. Here we are on the Oracle campus, just down the street from where these principles were first laid out. A generation later, we're surrounded by a global economy powered by that little set-top box technology. This conference, JavaOne, is iconic. It's always been a celebration about a technology that has changed the world but is not standing still. But most importantly, it's a celebration about you, all of you, the ones who raised your hands, the ones who didn't, the senior engineers, the junior engineers, the architects, the managers, the data scientists, the interns, the students, and the teachers. Everyone whose lives have been moved by Java. Java's humble origins started in 1995. Let's take ourselves back to 1995. The top song of the year was Coolio's Gangster's Paradise. The top television show was ER. Warcraft 2 and Command & Conquer came out. eBay launched. The PlayStation 2 launched, and the iOmega zip drive. And in 1996 came the first JavaOne. Admire the beauty of the first generation Duke and the computers in the Hacker Cafe, And over the years, Java grew. It grew, and it grew, and it grew. It grew to top pretty much every chart conceivable, and it stayed there for multiple decades. But it wasn't just a technology innovation, it became a cultural icon. It's been featured in things like the New York Times crossword puzzle. It's been on hit television shows like Silicon Valley and The Big Bang Theory, one of which is funny. I'll let you guess which one. It's been on Jeopardy not once, but 7 times. So something around this long, it must be collecting dust, right? Well, wrong. This ain't your grandma's Java. This is just a snapshot of many of the features that have been released in the last couple of years, and a little bit of a look forward into some of the features that we hope are to come soon. But what does this list of stuff mean? Do we just randomly choose things out of a hat or take votes online? Well, no. They mean that the JVM is getting better, faster, and more efficient with every release. That's the machinery that runs your application. It means that the language is embracing new architectures like data-oriented programming. It's not just for large applications, although it is excellent for that, but it's also for scripts, prototypes, and small apps. It's not just for senior enterprise engineers, although senior enterprise engineers love Java. It's also for students, hackers, interns, teachers. And finally, we have your back when it comes to protecting you from the threats of today as well as the threats of tomorrow, like post-quantum computing. And finally, number 2, we are ensuring that Java is a top contender for AI workloads, whether you are generating your own code using a GenAI service like Oracle Code Assist, or taking LLMs off the shelf and integrating them into your applications, or even training and deploying your own models. We're ensuring that the evolution of Java makes it great for all of these use cases. And to continue this evolution, we announced Java 24 today, and we're thrilled to have launched that this morning. You're going to hear all about Java 24 and the latest features throughout this conference and also other recent releases. It's action-packed, but before we get there, we have some special guests I want to bring on stage. George Saab, Senior Vice President of the Java Platform Group at Oracle and Chair of the OpenJDK Governing Board. And it is my honor and privilege to invite Scott McNealy, the founder and CEO of Sun Microsystems from 1984 to 2006, and his son, Colt McNealy, the founder and CEO of LittleHorse.io.
All right, thank you, Chad. Thank you, everyone, for being here with us this morning. Thank you, Scott and Colt, for joining us. So, Scott, you were there at the very beginning. That's it. What? Yeah, I like the T-shirt, by the way. Why don't you tell us a little bit about how it all came about?
Yeah, I wish I could talk to you guys for 2 hours. I could have stories. But this almost didn't happen. When we were interviewing we found Bill Joy, the best Unix guy, and we were so happy, but we wanted more engineers. And we were talking at the staff, and Bill Joy mentioned James Gosling. I said, who's James? He says, he's the greatest programmer in the world. I said, we've been looking for software guys. Why didn't you tell me? Well, we called him right on the phone from the staff meeting. We flew him out. He fell in love with Bill Joy and Andy Bechtelsheim, and they did Vulkan Mind Melds, and we hired him, and he was off doing great stuff. And then a few years later, I heard through the grapevine, CEOs only hear things through the grapevine, and he was leaving. I called him in my office. I said, James, sit down. Because I said, what's going on? He says, I'm leaving. I want to go do something consumer, something, in the billions, not the tens of thousands. And I said, no, you're not. He goes, what do you mean? You're not. You're not leaving. I said, you go do whatever you want, with whomever you want, however much you want to spend, wherever you want to go do it, go set up shop, and I will fund it until you're done doing whatever you want to go do. He looks at me like, really? I go, yeah, just anybody, anywhere, go do it. Now, get out of here. I said, I want you to come back in a week, show me your plan, tell me what you're going to go do, and then you got to come in every year and explain to me the progress you're making. He looked at me like I was on drugs, and he walked out. And he went off and he created, it was called Green, and eventually, what he wanted to do was build a clicker, because we all had 14 clickers on our desk or on our coffee table, and he wanted to have an integrated clicker, but he needed an operating system, but then he needed a language, so that's how he created Oak, which then became Java. He brought it out. We never did ship a clicker. We had a prototype that was about the size of a bread box. It wasn't very clever, but the Java language, the runtime, the garbage collection, the no pointers, you've seen all the lists, and I'm so excited to see the list continue to grow of what Java can do. And anyhow, we went over and had a meeting with some guy named Mark Andreessen over at Netscape, and he said, I got this browser, but it's static, it's just HTTP. And we said, well, throw this little runtime in there, and all of a sudden you got an interactive web page. And literally within the first few weeks, tens of thousands, hundreds of thousands of downloads of Java in the browser, and the internet was born. So that's sort of how it all happened. And I was actually looking at the languages from 30 years ago: C, C++, COBOL, Fortran, Pascal Basic, Perl, Assembly, SQL. Ada was in there being pushed by the government. Apple was pushing C#. You look at it, and Java is still top 3 in the world 30 years later. And I think it's number 1 with people who are doing real work and doing enterprise stuff. Little side note to all you managers, 4 times I had to go back into the budgeting process and put the funding for James' project back into, I said, that's the first thing we're funding. Everything else is secondary. And it was a real battle because people wanted to continue to do, I mean, there's just not a lot of Sun workstations around anymore. So I'm glad we got Java through the process. And by the way, there's about 50 people who claim they named it Java.
Well, Scott, we're certainly all very thankful that you had that belief in James and the team and that you got things started and kept it going. I think everyone in this room and all the people listening on the live stream are 100% behind that, so thank you. So I'm curious, Scott, the world has changed a lot since 30 years ago when Java was getting started. How, do you have any reflections on how things are different today?
Yeah, I think we were sort of uniquely positioned at Sun to go make this happen, but I do want to thank Larry and Safra for doing a great job. I think they kind of got out of the blocks a little rough the first few years until they sort of figured out what was going on, and some of the former Sun people finally grabbed control and said, listen, this is how it's going to be successful. I think one of the things we did very uniquely back then was the Java community process. And we actually, it was a really kind of a fun game because we got Jim Plu and Schlumberger and others to do Java Card for us, give us the technology back, and then we licensed it back to them at a fee. We had a whole bunch of people helping with the desktop stuff, and then we licensed it back to everybody on the desktop. We had IBM and DEC and others helping to do J2EE, and we had 100% of the Mars landing vehicle market. All one of those vehicles ran Java. So, but we had everybody helping us, and then we would put our logo on it, the Java logo, and then license it back to them for a fee. So it was actually a nice business. But I think we were uniquely able to do that. I mean, Microsoft, I'm supposed to not say anything bad. You're going to put me on stage and not say anything? Actually, I won't talk about .NET. I won't ever say Ballmer and Butthead again, I promise. The hairball, I just won't talk about that anymore. And anyhow, they must have been off visiting tropical islands or something, I don't know. But sorry, I couldn't help. Actually, I love Microsoft. It's being run by a former Sun exec now, and they've opened up. They've gotten way less closed in their environment, and I think they're good supporters now of Java. So I'm very, very excited to see Satya doing very good things with that company. But they were busy doing other things. Apple was very proprietary at the time. The mini computer companies were just scrambling, just not able to keep up. Dell, Compaq, Hewlett-Packard. What did I say about Compaq, Hewlett-Packard? A slow motion collision of two garbage trucks. I got in trouble for that one too. So I miss having the microphone, but anyhow, I do want to apologize for one thing though that Sun did, and I think that might be a nice lead-in to Colt here. Looking at him, I just wonder who the father is. But we made a mess because everything was very controlled on the mainframe and mini computers. And then we came along, TCP/IP, NFS, distributed computing, Java, all of the network is the computer. And then you throw in all these LLMs and you throw in all the microservices and all the rest of it. We tried to fix it with publish and subscribe and other things like that, and it just didn't get it done. And so now we have, Colt and I were just with the CEO of a little Philadelphia cable and
Wireless company?
Content company, wireless company. Brian is his name. And they have 1 billion devices on their network, and every one of them has a microprocessor on it. Now, how do you control, manage, orchestrate, conduct business with 1 billion devices in all of these different places? You know, the operating system handled the computer. A big move was VMware to kind of handle, you know, the virtualization of that. Then all of a sudden, Kubernetes is virtualizing the AWS. But who's virtualizing and managing all of these billions and billions of IoT and LLM and even humans in the loop on all these workflows we created an unbelievable mess, and that's the next thing that needs to be cleaned up, and it's probably a nice segue into, he's the smart one in the family.
I don't know about that, but I'm going to go off script for a couple seconds here and say hi to my grandmother, a very young and vibrant 97 years old.
Raise your hand, Grandmom, 97. And I have my beautiful wife. He doesn't have one yet, so if you can find Susan, and then my sister, Susan. So if you can find, he's so busy working, but he's big, strong, smart, good, really good guy. And I want grandchildren. So.
I wasn't going to go that off script, but yeah. So to tie up that thought, when I graduated and a couple years after taking AP Computer Science, studied computer science at Stanford, and then got into the real world, had a real job, I was like, wow, this is really, really hard. In college, everything runs on one laptop, and you can enjoy all of the traceability, reliability, debugging. You can just attach the JMX console to your processes and see all the threads. You can see where the bottlenecks are. But in the real world, your business processes span multiple services, computers, data centers. There's people involved. You have to wait. Processes take forever, and you can't just put a debugger on that. You can't just JDB that. So I went to my dad and I said, hey, why don't we go start something and let's try to create a new programming paradigm which makes it really easy to program a cluster of services and computers so that you can write business processes and processes that run across that vastly distributed environment that you created at Sun, and be able to debug it and trace it as if it was running on one computer. And naturally, I decided, well, I don't know if I had much of a choice, but it turned out to be a great decision. We decided to write the core runtime of this littlehorse.io system, which is open source, of course.
He understands how the will works. So.
I don't know about that, but we wrote the core runtime in Java because of I like free dinners. But it turns out that it was the best decision we've made so far at Little Horse. There's many different things. So we care about performance, obviously, and you're about to hear from the people who are absolute geniuses working on Java and what they have done to make garbage collection faster. Threads are now more lightweight. Startup times are faster, and Java is an incredibly good language for performance. I will not talk about other languages that we're not supposed to talk about today. And the language is constantly improving, becoming more concise, but the crazy thing is how compatible it is. And it's so easy. When you write an application in Java, that code is just going to work forever, right? I've heard that they inside Oracle, they test Java 1.0 jar files against the most modern JVMs. So if you write something, it will work. So I mean, as a CEO, I don't like it when my engineering team is spending most of their time on upgrading code. I did some work in another language. It's kind of like Rattlesnake, but won't go too deep into that.
Snake.
Yeah, it's a snake, and we spent a lot of time every time there was a new version released fixing our code and trying to make sure it worked. Then we deploy it to production and it breaks. But that just doesn't happen with Java. Java is so reliable, so performant, and it's really easy to debug things and make it work fast with stuff like the JMX. So it turned out that was one of the best decisions we made at Little Horse.
Okay, well, thank you so much for being with us. I think this is a testament to how one generation creates problems and another generation solves them. And I do want to say we really appreciate all that you've done to bring Java along throughout its history, and we're looking forward to the future here. So thank you.
One last comment. I'm retired and I'm just helping companies get started. If there's anything I can do to help the Java community, reach out. They know how to get a hold of me if I can help. Advisory roles or make some introductions or help you go sell this stuff, I'm happy to do that. I can't spend too much time. I only have 700 cows at my ranch now, and I can't do much except watch them eat. So if I can help you, in any way, shape, or form, I'd love to. Keep up the great work. You're doing great stuff, and thanks to Oracle.
Thank you, Scott. There you go. Okay, so today, the world truly runs on Java. We actually took a look at the world's top 100 companies by revenue and found that over 94 of them are using Java in their enterprises. And the list of companies that are powered by Java is not restricted to just the largest or the highest revenue. It also has some of the smallest, fastest growing, most innovative ones as well. Today, we're going to hear from some of those companies about how Java is powering their success. Your Uber ride to the conference or from the airport was powered by Java. Your Netflix and chill session last night was powered by Java. And we're also going to hear from LinkedIn, who are going to tell you about how that senior developer role that you're eyeing, that was probably, the information about that was brought to you by Java as well. But you might not know this, Scott mentioned it briefly, you probably are carrying on the order of 10 to 12 Java devices on you right now in the audience. I'll give you an example. Secure elements in smartphones powered by Java. Most smartphones have about 2 Java cards in them. Anyone have any credit cards? Those are probably also Java card. And maybe you've got a badge to get into your workplace that has RFID. That's probably also a Java card. In fact, it's hard to find a technology that's more pervasive than Java today. And as Chad mentioned earlier, we're just getting started. Today's release of Java 24 is the 15th release in the 6-month cadence. We started this in 2018. And now every March and September since then, like clockwork, you've been able to expect a new production-ready release of the Java platform. I think it's really hard to overstate the significance of this move to a fast release model. Over the last 7 years, we've learned to take bold, large problems and break them down into smaller deliverables that have been able to go into successive releases. And we've gotten feedback from you, from the early access builds from these projects, and also from the preview features that we put into the mainline releases. And all of those have helped form the final version of those features. We've been able to foster innovation in projects like ZGC, Amber, Loom, and Valhalla. And we've done all of this while staying true to our commitments to have security, stability, and backwards compatibility. And now I regularly hear, even from some of the folks who early on were skeptics of this fast release model, that they think the release cadence is the most important change in the history of Java. So for that reason, it really gives me a lot of pleasure to welcome someone on stage who was there in the beginning and seminal in helping us come up with this model. At the time, we had a little bit of a challenge because, as you may know, we've got a very famous luminary in our group whose name is Mark. And this person's name is also Mark, so we had to disambiguate them somehow. So we decided we were going to call him Crazy Mark. And we called him that because we were like, yeah, we're thinking of doing a faster cadence. And he was like, how fast? And we were like, I don't know, maybe every year? And he was like, no, it's got to be every 6 months. And we were like, oh my God, this guy's crazy. So with that, I'd like to welcome on stage Crazy Mark Cabbage, who is now the president of Docker, Inc.
Thanks so much, George. Well, that is definitely on brand. Little tough, but fair. All right, well, I am thrilled to be back here with you all. It has been a minute, I think 7 years since the last time, and it's amazing to see how vibrant Java is now, and amazing to see the progress. So, I'll be talking to you a bit about Java and a bit about Docker, because I love Java, but Docker loves Java. So, if you don't know, sorry, that was back one slide, please. If you don't know, Docker defined what it means to be container native, and our ecosystem shows that. We have over 24 million registered developers and over 14 million images across all types of languages and applications in our catalog. And in short, we see everything across the industry. And the numbers for Java, in my opinion, speak for themselves. We see over 8 million developers using Java, and those developers are working with the core images it takes to code a new application. This is things like OpenJDK, Oracle JDK, Maven, Gradle, et cetera, over 150 million times a month. So in short, what that tells us, and should tell you, is that Java's big and Java's vibrant. So We talk a little bit about where Docker's going and how Docker and Java are going to be better together. Docker, kind of since inception, has been working on solving the software supply chain problem. And what we hear today from everybody, whether it's individuals, teams, organizations, enterprises of every size, is that securing that supply chain is one of the biggest pain points, in particular when it comes to open source software. So we're building on our history of delivering trusted content and things like Docker official images and so on to give out new high-integrity building blocks and better tooling that lets you manage ultimately the provenance and trustworthiness of your dependencies. And what I will say is we know it's not enough to solve this at just the base container problem. You need everything from that to void main and all the dependencies in between secured. So we are super excited to start working with the Oracle Java team and eventually the Java community at large to solve this problem, and we're committed. So next thing I'll talk about briefly is AI. We have been investing a lot in this in the past few months, and I assume you all are using the frontier models every day. But if you don't know, local large language models are moving at a super fast clip. And we're fervent believers the world needs this, whether it's for cost, whether it's for privacy, whether it's for performance, whether it's for flexibility, any number of reasons, we think this is just a fundamental thing that the world needs. So as of today, we are making that much, much easier to do in containers, and we're making it much easier to build, test, fine-tune, and ultimately use local large language models. So what do we do? Today, we now have in Docker curated large language models. This is things like Mistral, DeepSeek, Llama, et cetera. And with something as easy as any other Docker run command, you can now run those anywhere you run Docker. And when you do that, you're going to get an OpenAI compatible API. That means your standard libraries like LangChain4j, Spring AI, et cetera, will just work. So that's cool, but we didn't stop there. We wanted to make sure that your desktops, all the way when you're iterating on these things every day at home or at work or wherever, are screaming fast. So we're giving you out-of-the-box GPU acceleration on both Apple Silicon and Windows NVIDIA machines, which of course will translate to prod when you get there. And then maybe the biggest thing in my opinion is we did all of this with standard OCI, that's Open Container Initiative, format images, so you can push these things and pull them from Docker Hub natively and other container registries. We think this is going to change how people are using LLMs. We think it'll help you as Java developers go much, much faster. I'm super excited to see what you do with it. Everything I'm describing right now is in Docker Desktop nightlies today. If you don't want to live on the bleeding edge and you want to wait 2 to 3 weeks, you can sign up to be notified at docker.com/LLM. And I'll leave you with this. Over the next year, the next couple of months, we're going to be shipping a lot of stuff at Docker. We're invested in developer productivity, in security, in AI, and some other things. And importantly, we do love Java, and we are deeply committed to making sure that Docker and Java are always going to be better together. So, with George,
All right.
floor is yours.
Thank you, Crazy Mark. I think you'll agree with me. It's always reassuring to know that there's someone crazy at the helm. Okay, so Chad showed you a list before of many of the features that we brought into the 6-month feature releases. But as we like to say, not every hero wears a cape, and in our case, not every improvement gets a JEP, right? In fact, each of these releases is packed with lots of smaller changes. Taking a look at the release notes is a very good way to find out about them. And some of them we will just talk about in situations like this. So here's an example. Take a look at the G1 GC memory footprint improvements from JDK 8 to JDK 24. Now, in this case, the lower line, the better. And as you can see, GC memory usage is now just a fraction of what it was in 8. So just moving forward can give you access to some of these benefits. But I don't want you to just take our word for it. I think it's always nice to have a real-world example. And here to give us an example of how GC improvements are making a difference for them, we have Mingmin Chen, the head of Uber's real-time data and search platform. Okay, thank you for joining us, Mingmin. Why don't you, just tell us how you're using Java at Uber and how it makes a difference for you?
Cool. So first off, I do want to do a quick poll. How many of you use Uber or Uber Eats in the past, say, 30 days? Wow, almost everyone. Cool. Awesome. So at Uber, we use Java a lot. It's heavily used in our tech stack, right? It's one of the most primary programming languages in our backend development, right? If you look at our core tree flow, many of our core services, microservices, are written in Java, right? Roughly 50% of the services. We are talking about thousands of services that are written in Java. And if you treat Uber as a vehicle, the underlying engine is actually the data and storage stack. And our data stack is using a lot of open source technologies such as Kafka, Flink, Spark, Presto. All of these technologies are Java-based, JVM-based, right? So Java is actually powering the data stack and essentially powering Uber's business, right? Now let's deep dive into one particular use case that we have, which is the real-time log search and analytics. We built it on top of Apache Pinot, right? As you can imagine, logging and observability is so essential in engineers' day-to-day life, right? Engineers use logging for their troubleshooting, for debugging, and monitoring their services, right? Here is a screenshot that I take from an internal service that we have. And the logs, as you can see, right, a lot of logs coming in ingest to our data stack. So, we have very high ingestion volume, right? And then if you look at how people use logging, queries could be ad hoc, right? And then the queries could be, touching the data, some of them could be hotspot, which make it very hard for us to debug some of the challenges like tail latency issue, right? But if we did dive into the tail latency issue, we notice there are some pattern. One, of course, there are long GC pauses, right? And then there are high timeout and error rate. So we take a pause and realize that maybe we can look at the GC tuning, right? Because that could potentially help solve the tail latency issue. So at the time when we debugged the issue, we were using Java 11 and JavaOne GC. So after a few rounds of tuning, we got some very good result. We used generational GCC in Java 21, right? And as you can see in this slide, right, we reduced 50% of the latency for the tail queries. And we also reduced the CPU utilization, reduce the memory footprint, and if you look at the usage, right, it's less spiky, it's more smooth, and basically the new GCC, generational GCC, is actually making our queries better, faster, and more efficient, right? I would encourage all of you just to try out like new Java releases, right? There are a lot of new features, enhancements, that you will get a lot of benefit. Always try to be probing. When you deep dive, you will get a lot of good learnings and results. And feel free to talk to me if you want to learn more how we do the tuning. And also, Uber is hiring Java engineers. Talk to me afterwards. All right.
Okay, thank you so much.
Thank you.
Thanks for being with us. AI is changing the landscape of software development. And we're seeing this in three key areas: code generation, model integration, and use of models. So for code generation, Java is a great language due to its strong typing, memory safety, large amounts of training data, and its focus on readability. In fact, Gen AI services like Oracle's Code Assist can be your pair programmer today. For model integration, we see tools like LangChain4j and JLlama that make it a snap to integrate a variety of leading LLMs into your core business applications, most of which are probably already written in Java. And if you're thinking about use of models, the Java platform is evolving quickly with projects like Panama, Valhalla, and Babylon to become a trusted AI engineering platform. In fact, we're going to see a demo of some of that work very soon. And speaking of the future, Java's flexible programming model and straightforward standard library have always been a strong foundation for students to learn and educators to teach. For a couple of years, we've been talking about a concept that we call paving the on-ramp. And that's intended to smooth the curve of learning for new learners to get onto the highway of being a full-time Java developer. From simplifying the student's first program to a new and improved redeveloped print loop experience in the Java playground at dev.java, we've been ramping up investments in order to help the next generation of developers. So like many of you, their first exposure to Java may have been through the Advanced Placement CSA exam in high school. This first impression is critical, and to talk about how the AP CSA is itself modernizing and paving the on-ramp, I'm very pleased to invite Edward Biederman, Executive Director of the AP at the College Board, and Heather Stevens, Senior Director of Java in Education at Oracle.
Hello from the AP program. George says innovating and modernizing, and those may not be the first two words that come to mind when you think back to your high school experiences, when you think back to stodgy paper and pencil AP tests that you might have taken in high school as 15, 16, or 17-year-olds. And that's fair. That's totally fair. AP exams are solid, steady, stable measures of student mastery. So when Oracle tells us that they'll be updating Java every 6 months, the AP program takes notice. You see, the Java has been the official programming language of the AP Computer Science A exam for over 20 years. Back then, it was Java 1.4. But there's a lot of work that needs to be done. It's exciting to be here, part of the release of version 24. But teachers that teach AP Computer Science A are still using Java 8. So this fall, we will be updating the AP Computer Science A course, and we'll be asking teachers, encouraging them, and supporting them at the start of the year, each year, to be using the latest version of Java. And that's really the modernization that George is talking about. But we'll need help, which is why we're here. We're very happy to announce a partnership with Oracle.
And I speak for everyone in this room, I think. We care deeply about nurturing the next generation of Java developers, so we're excited about this partnership too. I think AP CSA is an excellent starting place for kids to gain fundamentals in computer science with modern Java, and it's a great first step towards a modern career in computer science, and also just life, right? This is our life now. I love that you all are training the teachers and helping them get the skills and knowledge they need to teach the kids. And I'm especially excited about the labs and the idea that we can do things together that make problems for kids to solve that are relevant to them. It's just really exciting. So thankful.
Thank you. We're also equally excited. We're ready to roll up our sleeves to do just that. George, the program is feeling particularly bullish about this partnership and what we can do. Every year, AP contributes 100,000 students to the pipeline of computer science college majors. In fact, AP Computer Science A is offered in 1/3 of all high schools that participate in the AP program. But what if we could double those numbers? What if we could expand the reach of computer science education and also get teachers and students connected to the latest versions of Java? So thanks for letting us be here to share the update about what's happening in the AP program. Congratulations on your version 24. And to all of you in the audience who may have a high schooler at home or have a high schooler in your families that will be taking AP Computer Science A, you can tell them that the latest version of Java is coming to them too. Thank you.
All right. Thank you for that update, and to my 10th grader, if you're watching on the stream, take note. Okay, so we've gone through a lot of real-life cases. We've talked about where Java is headed. I think it's time to roll up our sleeves and kind of get into some technical detail here. What do you think? Yeah? All right. Well, to take us through that, I'm very, very happy to present the chief architect of the Java platform, Mark Reinhold.
Hey, George. Good morning and welcome to JavaOne. Isn't it great to be back? Yeah. Yes. As George mentioned, this year Java will be 30 years old. Wow. And I've been working on it for most of those years. After 3 decades, Java remains one of the most popular programming platforms in the world, used by millions of developers to build mission-critical systems for organizations large and small. Why has it been so successful? One part of the answer has been our relentless focus on 2 big goals. One is developer productivity, that is helping developers build and maintain large and reliable programs. The other is program performance, whether performance is measured in startup time, warm-up time, latency, throughput, or static or dynamic footprint. We pursue these goals in the face of constantly evolving programming paradigms, such as mixed functional and object-oriented programming, evolving application areas, big data, machine learning, and AI, evolving deployment styles from on-premise to the cloud, and evolving hardware, terabyte memories, deeper memory hierarchies, vector and GPU instruction sets, and deeper and more numerous processor pipelines. Now, as important as the goals we choose are the means by which we work to achieve them. Another key to Java's success, I think, has been the fact that that we take the time to think about the big picture and the long term. We don't act only as developers, that is, people who create things. We also try to act as stewards. We try to be responsible for overseeing and protecting something considered worth caring for and preserving. We try to preserve the past while evolving for the future. Our stewardship of the Java platform is guided by 2 key values: readability and compatibility. My predecessor, Graham Hamilton, elucidated these values back in 2005. About readability, he made 3 main points. Reading is more important than writing. Simplicity matters. And Java should be one language with the same meaning everywhere. Why is readability so important? Well, readability is essential to maintainability, and Java has never been about write-only, throw-away code. A more condensed statement of this idea, which I've always liked, is due to Abelson and Sussman of MIT, who wrote, "Programs are meant to be read by humans, and only incidentally for computers to execute." Graham also discussed compatibility with respect to evolution. We will evolve the Java language, but cautiously with a long-term view. We will add a few selected features periodically. He wrote here of the language, but these principles apply equally well to the entire platform. Readability, compatibility. With respect to compatibility, there's the familiar trio of source, binary, and behavioral compatibility. I think we all know what these are, but source compatibility means that existing code continues to compile. Binary compatibility means that existing code continues to link and run. And behavioral compatibility means that existing APIs continue to behave in the same way with respect to their specifications. There are at least 2 other important aspects of compatibility for Java, I think. One is what we've come to call migration compatibility. Migration compatibility means you can adopt new features incrementally without flag days where you have to change your entire code base all at once. We first achieved this with generics in Java 5. We did it again with lambdas in 8 and then modules in 9. Perhaps the most important type of compatibility, though, is what I'll call intellectual compatibility. This means that new features build on existing knowledge rather than destroy it. After all, millions of developers have invested countless hours learning how to use the Java platform effectively. To preserve that investment, we must carefully balance conservation and innovation. We must respect the past, but not be unduly constrained by it. We will add selected new features, but we must strive to make them look like they've been there all along. Most of all, we must have the guts to say no. To follow some of the best advice ever from James Gosling, we must have the courage to do no thing rather than the wrong thing. Preserving our values while pursuing our goals is much, much harder than it looks. But that is what we've been doing for almost 30 years, and we will continue to do so. Now, when it comes to improving developer productivity and program performance in a constantly evolving world of technology, how do we decide what to work on? The answer is actually pretty simple. We look for pain points. When faced with a programming task or a performance problem, what makes developers sad? Because they think another language would be better. Or what makes them roll their eyes once again, as they crank out yet more boilerplate code just like they did yesterday, one more time. Or what makes them angry because they just can't get the job done in a reasonable way at all. Thinking about pain points and evolving technologies and our goals and our values leads us eventually to propose solutions, which arise as new features which surface as JDK enhancement proposals in the OpenJDK community. Now, some pain points are so acute and some solutions are so involved and broad that we create entire new projects for them in the OpenJDK community, each of which produces a series of JEPs over time. So let's look at some pain points and our solutions to them. Java's too difficult to teach. We heard a little bit about this earlier. To see what I mean, close your eyes, cast your mind back to when you were first learning to code. Your professor, your teacher, or the book you were reading on your own starts with a simple exercise. Here it is. Open your eyes. This simple program prints hello world. But what is all this? Public class hello? Why is it class? What's class? Why is it public? Public static void main, that's public too, but it's static. Oh, when it's void, why does it do anything at all? System out println, why can't I just write print? Come on. We're tackling these problems in Project Amber in an effort we call paving the on-ramp, which George described earlier. We aim here to provide a graceful on-ramp with a gentle slope from simple programs to full applications. Public class, public static void main, system out println, these somewhat odd incantations serve a useful purpose in larger programs. To a beginner, however, they are deeply mysterious. So to pave the on-ramp, let's see if we can do without them. First, we remove the need for the main method by extending the Java launcher to look for a non-public main method and instantiate the enclosing class before invoking that method. This is called an instance main method. Second, we remove the need for an argument array by extending the launcher further to look for zero-argument main methods. Now, don't worry. For compatibility, the launcher will prefer a public static void main method if one exists. Third, we remove the need for the class declaration by introducing a simple form of source file that lets you get straight to the code. We're not done yet. Fourth, in such source files, we automatically import a few useful methods for console input and output, thereby simplifying the infamous system out println simply to println. Not bad. We considered whether we could get rid of void and main and decided that would just be too bizarre. It would actually put a giant pothole in the on-ramp, so we didn't go there. Now, where does the println method come from? Println is declared in a new class in the Java I/O package, which is named, naturally enough, I/O, all caps. We can shout I/O. It declares methods for printing to the console and reading strings from the keyboard. Now, with these readln methods, you can move on to your second programming exercise, which asks the user for their name and then prints a greeting. We can put this program in a file and then run it with the source code launcher, and it asks for my name, which I type, and then it prints the greeting. Let's consider a slightly more sophisticated example, shall we? This program constructs a list of the first names of the authors of the Java language specification and then prints out the length of each name. It must import the JavaUtil list class, of course, because that's just one more confusing concept for a beginner. We eliminate the need for the import by arranging for simple source files to automatically import every package exported by the Java base module. Now, that's a lot of packages, but it turns out there are surprisingly few conflicts amongst the classes and interfaces which they contain. It's like as if we had planned it, but we didn't. Returning to our example, providing a smooth on-ramp means making it easy not just to write small programs, but also making it easy to grow small programs into larger ones. We can, if we want, put this program into a class, and then add an explicit static wildcard import of the IO class for the println method. But now, what do we do about the list interface in the JavaUtil package? We could add an explicit import for that, but in a medium-sized program that makes broader use of the APIs in the Java base module, that could be tedious. So we instead use a module import declaration, which does just what you think. As a side note, we can use the original program as a launchable single file source code program by adding the shebang line, placing it into a file, making the file executable, and then running it. Now, we don't expect beginners to do this, of course, but experienced developers write small programs too, right? They can also benefit from zero-argument instance main methods in simple source files that automatically import many useful APIs. And combined with the shebang construct, experienced developers might even see this approach as a pleasant alternative to shell or Python scripts. I know that I do. These initial on-ramp features are brought to you by two closely related JEPs, module import declarations, and simple source files and instance main methods. These are in Java 24 as preview features. So if you're interested, please try them out and send feedback. There are more to come. This is only the beginning of the on-ramp. Okay, let's consider another pain point. Threads are too expensive. Okay, well, wait. Okay, we got virtual threads in Java 21. Mark, this is old news. Why are you telling us about this now? Well, virtual threads are great. They're lightweight threads implemented directly in the VM. They eliminate the need to use complex and difficult to debug non-blocking or reactive programming models in order to achieve high scalability. Been very successful. They scale quite well. Here, for example, is the TechEmpower web framework benchmark running on Helidon IO. As you can see, in its third release running on JDK 21, at that time, Helidon was still based on the Netty IO framework, and we normalized the performance here to 1. Helidon 4 is based on virtual threads, and in JDK 21, it got a 78% performance boost, which is pretty good. And it got a little better still in 22 and 24. But there was still a pain point remaining. Virtual threads don't scale when I use the synchronized keyword. Yes, we knew this when we shipped virtual threads in 21. We warned people that it was going to be a problem, but we thought it was best to get it out there so that people could use it because there were effective workarounds. I'm happy to report that as of JDK 24, those workarounds are no longer necessary. We can now synchronize virtual threads without pinning, and they scale great. All right, another pain point. Garbage collection pauses are too long. Let's look at some data. Here's a graph of pause times while running the SpecJBB 2015 benchmark with the parallel garbage collector. Now, you might be wondering what these bars mean if you haven't seen a graph like this before. When analyzing the response times of any kind of system, it's important to pay attention to the distribution of latencies, and in particular, the high percentile latencies, or tail latencies. These can help us understand how the system degrades as its load increases. Now, you can see here the average, the 90th, the 95th, and 99th percentile latencies aren't so bad, but 99.9 there is getting pretty horrible. The G1 collector does a little bit better, but to really solve this problem, we introduced the highly concurrent Z garbage collector in JDK 15. Yeah, that really is the data. Its latencies are so low that it's hard to see what they are. So let's switch to a logarithmic scale, and there you go. You can see that ZGC's highest tail latency for this benchmark is well under 10 milliseconds. That's not bad. Even better, ZGC's pause times are independent of heap size. But we could do better still. By JDK 17, we had made thread stack scanning concurrent, achieving sub-millisecond pause times, even in the highest tail. That's impressive, but there was a remaining pain point. ZGC scales poorly on some workloads. Here's one of them. This is an Apache Cassandra benchmark. The number of clients increases on the x-axis. Latency is shown on the y-axis. G1 holds reasonably steady as the number of clients increases. ZGC, however, fares quite poorly, with latencies approaching an entire second at the end there. Now, it might seem surprising that G1 beats out ZGC here, but the reason is that this benchmark creates many, 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 many short-lived objects. And G1 is generational. ZGC is not. At least it wasn't at that time. We implemented the obvious solution to this problem and made ZGC generational in JDK 21. Here you can see that its tail length latencies are far better. So if ZGC is so great, why do we need any other collectors? Shouldn't we just deprecate them and remove them and have less code to maintain? Well, no. The art of garbage collection is all about trade-offs. ZGC's low latencies come at the price of higher memory consumption for its data structures outside of the heap. It requires over a gigabyte of data for this benchmark, whereas Parallel and G1 use about a third of that amount. There are also, of course, trade-offs between Parallel and G1. Parallel is optimized for throughput rather than latency. G1 is mostly concurrent, so it has better pause times than Parallel, but also less overhead than ZGC. Owing to all these trade-offs, we have also continued to improve Parallel and G1. We have significantly improved their throughput. Using the same benchmark, here are their relative throughput scores for JDKs 8, 17, 21, and 24. As you can see, each collector has about 30% higher throughput in JDK 24 than it did in JDK 8. We've also significantly improved their latency. Here are their relative latency scores for JDKs 8, 17, 21, and 24. Parallel's JDK 24 score is over 60% better than in JDK 8, and G1's score is 90% better. There are two lessons here. One is choose your garbage collector wisely, appropriate to the performance requirements of your application and the hardware resources available. Second, keep upgrading to new releases, even if you never take advantage of any new features. You might get a significant performance improvement with little effort. Now, benchmarks are, well, benchmarks. So to tell us more about garbage collection in the real world, I'd like to welcome Paul Bacher of Netflix. Hey, Paul, how are you?
They probably recognize this screen. This is the Netflix app, and this is the screen where you choose what next show you're going to watch. This screen and most other things at Netflix are all powered by Java. And if you take a look at our architecture, we currently have a federated GraphQL architecture where there's like one giant GraphQL schema from the perspective of a client, in this case a TV. But in the backend, that schema is actually composed by many different microservices. And these microservices are all built on Java using a Spring Boot framework and a DGS framework. And we have over 3,000 of those services. So that means Java is a really, really big deal for Netflix because pretty much everything we build is built on Java. In the last couple of years, we made a really big push to upgrade all our services to JDK 17 or newer. And of course, we got all the benefits of the new language features. But another thing that we noticed is that we were spending about 20% less CPU time on garbage collection after we upgraded to JDK 17 from JDK 8. Now, this is on the same G1 garbage collector, so nothing changed, no code changes, no configuration changes. And we got all this performance basically for free by just upgrading our services to the new JDK. Now, the story doesn't end there, because, of course, we have newer Java versions as well. And starting with JDK 21, we started experimenting with generational ZGC that Mark was just talking about. Now, typically, before we switched to ZGZ, what we were seeing is that with G1, we were getting frequent pass times of like a second to a second and a half. And at that point, what would happen is that IPC calls that would go into the service would start timing out. So they would time out, and now we get into retry behavior, and it just adds additional load onto our clusters. Now, we were mitigating that, but of course, it would be better if you don't have to deal with that. So when we changed to ZGC, what we noticed is that those pass times are entirely gone. And it's in effect, the error rates of our IPC calls are just much lower. Well, fewer errors is of course better. And it just makes our services more reliable, easier to operate, and we can just squeeze a lot more performance out of those services. And again, this is mostly just by upgrading it to the newer JDKs. And that's what we continue doing. We keep upgrading to the latest versions of the JDK.
Okay, great, Paul. Good story. Thank you very much. All right. Let's consider another performance pain point. Java programs sometimes start up too slowly. The goals of Project Leiden are to improve the startup time and the warm-up time of Java applications. Startup time, by that we mean the time needed to get to the first useful unit of work, for example, the first HTTP response. Warm-up time means the time needed to reach peak performance. Now, Java has historically favored peak performance over fast startup and short warm-up. Most initialization code is run by interpreting bytecodes while the hotspot JVM profiles the application's behavior to figure out how best to compile those bytecodes to native code. All of this work can take a while. Once hotspot does that work, however, it can achieve highly competitive performance. Now, the basic trick to improving startup and warm-up is to shift some of that work either earlier or later in time. Earlier to a time before the application starts, or later to after the application has warmed up, or in an ideal case, maybe never. How do we figure out how to shift work earlier or later? Well, generally speaking, there are two approaches. One is to statically analyze the program at build time to figure out which work can be shifted. This can be surprisingly effective, especially if you're willing to accept constraints that require changing your code. But it can't adjust to changes in application behavior over time, and builds on this approach can take a really long time. The second approach is to observe the program at runtime in a training run and apply those observations in a subsequent run to shift work to build time or to some later time. These optimizations are based on actual application behavior, and build times are short. Now, in the big picture of Project Leiden, we intend to explore both approaches, but to get started, we wanted to answer two questions. How far can we get without imposing new constraints on existing code, without making any specification changes, and without sacrificing any of Java's natural dynamism? Second, how far can we get simply by leveraging existing hotspot JVM components? So for now, we're not doing any static analysis, and we're relying on training runs to gather observations dynamically. In more detail, here's how training runs work in Leiden. Step one, training. In this step, we record observations of the application in action, which classes does it load and initialize, which methods become hot, all those sorts of things. This results in a configuration file, here in blue, called app.aotconf. Step two, assembly. We convert the observations into an ahead-of-time cache, app.aot there in orange. Step three, profit. We run the application with the AOT cache and hopefully enjoy better startup and warm-up. Now, those of you familiar with the existing class data sharing feature, CDS, might recognize this pattern. Our AOT work is, in fact, in part, an evolution of CDS, which has been around for a really long time, goes all the way back to JDK 5. Now, this workflow is a bit clumsy. We've already prototyped a simpler workflow. In any case, frameworks and build tools can help with this. For example, a CI system could use integration tests for training runs. We might eventually figure out how to collect training run observations in production in a very efficient way. We'll see. So exactly what sort of work can the Leiden JVM do ahead of time? Well, quite a lot, it turns out. It can load and link classes, it can profile methods, it can resolve constant pool entries, it can compile bytecode to native code, it can generate dynamic proxies, it can generate reflection data, and it can cache class not found results. We delivered the first optimization, AOT class loading and linking, into JDK 24 as JEP 483. We've implemented all of these optimizations in the Leiden early access prototype builds. We're currently working to productize and integrate those into the JDK mainline in subsequent JEPs. So how well does all this time shifting work? Let's look at some numbers. For a simple Hello World application running on the Helidon web framework, if we normalize its startup time on plain JDK 24 to 1, then with the AOT class loading and linking feature in JDK 24, we get a significant improvement in startup, about 65%. Using all the additional AOT optimizations in the Leiden early access build, we get an additional 9% improvement in performance. We see similar results for Hello World applications in Micronaut, Quarkus, and Spring Boot. You might be wondering about our focus here on simple Hello World applications. In the fullness of a web framework, they're actually not trivial. They're way more complex than Hello World on the command line. Besides, we have to learn to walk before we can run. We have measured the benefit of these time-shifting optimizations on a more realistic application, namely the Spring Pet Clinic demo application. Here, the relative benefit of AOT class loading and linking is somewhat less, but the relative benefit of the other optimizations, in particular ahead of time compilation, is greater. This is not surprising. Simple Hello World applications benefit less from ahead of time compilation because, well, there's less code to compile. So Leiden has already delivered compelling performance gains with more to come. It does all this while remaining fully compatible with the specification of the Java platform. Existing applications just work. There are no new constraints. There are no new constraints on how you write your code. There's no need to adjust your code to adapt to new constraints. Limit yourself to using libraries whose maintainers have adapted their code to new constraints, or generally worry that your application will behave any differently other than to start up and warm up more quickly. All right, one more pain point. Using native libraries is too hard. Why is this important? I mean, everything should be 100% pure Java, right? Well, no. There are many useful native code libraries out in the world for cryptography and numerical analysis and machine learning and AI, all sorts of things. None of these libraries will ever be rewritten in Java. But we should be able to leverage them from Java, right? Java's current answer for this is the Java native interface, JNI. It goes all the way back to JDK 1.1. JNI is both difficult to use and slow, which is intentional, by the way. To see what I mean, consider the question. What's required to call the C library's getPID procedure from Java code? That's the procedure that just returns the numeric ID of your process. Well, you have to write a JNI wrapper in C code for the procedure. You have to write a small Java source file to declare the corresponding native method. You run that file through Java C to generate the C header file. You need to compile the JNI wrapper that you wrote a minute ago. And then once you compile the wrapper into a suitable native code library, you can finally call getPID from a Java program. Whew. The whole workflow is just cumbersome and involved. As a result, Java bindings for many popular native libraries either don't exist or they're slow to be updated. For example, TensorFlow is a popular machine learning library written in C++. It does have a Java API binding, but that binding comes with a warning. Caution, the TensorFlow Java API is not covered by the TensorFlow API Stability Guarantee. As a potential user of this library, that does not instill confidence. To make native code easier to use and native data easier to access, in Project Panama, we created the Foreign Function Memory API finalized in Java 22 via JEP 454. This API in the Java Lang foreign package allows you to allocate and deallocate foreign memory, manipulate and access foreign memory in a structured way, call foreign functions from Java code, and arrange for foreign functions to call Java code. The FFM API is both safer and more efficient than JNI. In Project Panama, we also created JExtract, a tool which mechanically generates Java Lang foreign bindings from native library headers written in C or C++. Now, to call the C library's getPID procedure with the FFM API, you start with the C header file that declares it. You run that through the JExtract tool to generate a Java source file that declares corresponding FFM bindings. Those bindings refer directly to the C standard library. You don't need to write native code wrappers. You don't need to compile them into native libraries. No other files are required. Calling getPID from Java, then, is a simple matter of importing the bindings and invoking the native method. To learn more about using the FFM API and JExtract in a richer setting, I'd like to welcome my colleague, Paul Sandoz.
Hello.
Hey, Paul.
Hi.
What do you have to show us?
I'd like to show a machine learning application written in Java that can predict what number is present in an image of a numerical digit.
I'm detecting a theme here, because that's like the hello world of machine learning,
It is.
right?
We are learning to crawl. It's a type of application you choose when you're learning to crawl before you can walk and run. And we're definitely in the crawling phase as we're building out a prototype machine learning library and building an application on top to predict numbers.
So why did you choose to do this?
Well, two reasons, really. First is we want to show what we can do for machine learning with the foreign function and memory API, together with a feature called code reflection that we're working on in Project Panama. And second, we can evaluate whether those features are fit for purpose and then learn from that and improve them.
So code reflection, that's a new term. What is that all about?
Yes, code reflection is all about giving access to Java code in a new symbolic form, being able to translate that code, which can then be mapped to foreign programming models such as GPUs, machine learning models, automatic differentiation of those models, parallel graph programs, databases, ... Think of a crazy use case. So it allows you to leverage those models, foreign programming models, directly in Java without having to write your code in a different language, probably lower level, and embed that code in strings or text blocks in your Java program. I have done this many times. You can think of it a bit like C#'s LINQ, but on steroids.
Okay, so in this application, you're using Project Babylon's code reflection to reach out to a foreign programming model, and then Project Panama's foreign function and memory API to reach out to native data in a foreign library.
Yeah, that's exactly right. So we're leveraging a native machine learning platform and interoperating with its programming model and its runtime.
So before we dive into the demo, maybe it'd be helpful for the audience to give a quick overview of machine learning and the platform that you're using.
Yes, this is a 101 overview of machine learning.
Okay, yes. Hold on to your hats.
Okay, so at an abstract level, a machine learning model is just, and that just is doing a lot of work, a mathematical function that performs predictions. That's it. For example, the model could predict what number is present in the image of a numerical digit. The function could take as input all the elements of an image, in this example, roughly 800 inputs, and output 10 values corresponding to the probabilities that the digit is a particular number. In this case, the function predicted correctly the digit is the number 7, since it has the highest probability.
So how do we implement such a function?
Okay, we implement the function with two components. The first is just code that consumes and produces tensors, which are just a fancy word, in that case, for multidimensional arrays. And second, a bunch of data called weights, which are also just tensors. That's it. There's nothing particularly magical about what is going on, though the code might be computationally expensive to execute, and the weights might consume large amounts of memory.
So where do the weights come from?
They come from a process called training. Training computes the weights, executing the code multiple times, with known inputs and outputs, and optimizing the weights for the best results. And once we have the weights, inference is a process of executing the model or the code with brand new inputs.
Okay, so tell us about the machine learning platform that you're using.
Okay, so we are using a machine learning platform called ONNX, which stands for Open Neural Network Exchange. It's really just two things. It's a format for representing models and a runtime for executing them. So you can think of ONNX models as a constrained form of code plus constant data, that is the weights we just talked about. And ONNX enables cross-platform execution of machine learning models independent of the platform that was used to develop and train them.
Okay, so you're leveraging ONNX and interoperating with its programming model and its runtime.
Yeah, correct. Using ONNX and modern Java features, we're able to rapidly build a prototype machine learning library in Java. And here is a diagram describing the architecture here.
Okay, and the native Onyx runtime is way down there at the bottom, and
right.
it looks like all the rest is Java code.
Yes.
That's great.
That's right. We can use Panama to bind to the Onyx runtime API, and using JExtract, like you mentioned. And then on top of that, we can just build an ordinary library that does the magic of transforming Java code into Onyx models, and then we can build an application on top of that.
Okay, ready for a demo?
Yeah, let's see if the demo gods are with us here. All right. Okay, so I'm going to run the demo. So remember, this is going to predict numbers. And I'm going to put in a number. First, I'm not very good at doing nines, so I'll just draw the 9, and then I'll run the prediction. And look, it gets it wrong. Who knew that machine learning models get things wrong?
Shocker.
Yes. So it's just my 9s, it doesn't like them, but I'll do another one instead. I'll do a 7, like this. And really, yes, it got it right. So I got it right. So it's a fun application that we built. But I feel like we should look at the code.
Let's look at the code. You make that a little bigger?
Yes. Let me zoom in.
Excellent.
Is that good?
Yeah.
Yeah.
Yep, that looks like our ordinary Java code.
Yeah, it's just plain boilerplate. It's not boilerplate code, sorry. It's just ordinary Java code. And what the Swing application is doing when we start it up, it creates an instance of this class called MNIST model, and it loads all the weights we talked about before from disk or from resources. And then every time we do a prediction, we call the classify method.
So that method is creating a tensor from the image of a digit and then passing that tensor as the input to the model.
Yes.
Okay.
So you can see the flow through. We've got the image data, we're creating a tensor from it, and then we're calling the Onyx execute. And really, the machine learning model is encapsulated in the lambda expression here. And the bulk of the work is done in the CNN method, which operates on the input tensor, and sometimes it operates on the weights we created previously.
So that Onyx runtime execute method seems to be doing some heavy lifting.
It is. There's a lot of work going on in here. So on first execution, what we do is we do the translation from the Java code to the Onyx model. And we do this in stages. First, we transform the Java code to a Java code model. And then we transform that to an Onyx code model. And then we transform that into the protobuf form of the Onyx model. And then we deploy the Onyx model to the Onyx runtime and execute it. But on subsequent executions, we only need to do that once.
But all those steps are automatic, right? Yeah.
Yeah. That's
okay,
right.
so I noticed there was some debug output from the application there that
Yes.
looks like the code models, maybe?
Yes, we serialized out the text form of the code models. You don't have to look too closely, but there's a Java code model flying by. And we transform all that code into an Onyx code model as we scroll down. Here it is.
Yeah, is there maybe a better way to look at this?
Yes, absolutely.
It's like line noise.
So yes, it's useful for debuggers.
Who knows what line noise is?
Yes. So we also output the Onyx model we created when we did this transformation, and we can view that using a tool called Netron. So I will open that in Netron. And so let me just open that there, like so. And this is a Netron tool viewing the model that we had in Java code. And you can see the conv and the gem calls, and you can see the weights being used by the conv operation and the gem operation. So the names we used in the Java API just so happen to be the names of Onyx operators.
Coincidence.
Yeah.
Wow. Okay. Very cool, Paul. Thank you very much.
Thank you.
All right. In the time remaining, let's quickly look at a few more pain points and our solutions to them. Quantum computing will break RSA. Yes, it will. We just don't know when. And in the meantime, people might be collecting encrypted streams and waiting until they can decrypt them at that future point. We've been preparing for this for a long time. We started, in fact, back in JDK 21 with the JEP for a key encapsulation mechanism. This is one of the multitude of cryptography standards relevant to post-quantum cryptography. We moved on in JDK 24 with a trio of additional JEPs, key derivation function API, quantum-resistant module lattice-based key encapsulation mechanism, and a quantum-resistant module lattice-based digital signature algorithm. These are all many words. These are complex technologies, but we've got them under control. There's a bit more to come, and as we did when TLS 1.3 came out, we are implementing these features in the current tip release, but in a rare case of backporting new features to older tail releases, we will eventually backport these to past LTS releases, because defending against post-quantum crypto is just so important. The Stream API isn't fully extensible. Yes, it's annoying. Well, now in Java 24, we have stream gatherers in the Java util stream package. If you want to write your own intermediate stream operations, now you can use a gatherer. My favorite bytecode library breaks on JDK 24. Yeah, well, stop using it. Use the class file API, JEP 484 in the JavaLang class file package. Writing raw HTML in java.comments is tedious. Yes, it is. It is so 1995. We're just totally over it. And now you can write java.comments in Markdown. JDK 23, JEP 467. And finally, you're not delivering new features quickly enough. Well, we have a couple of answers to that. And they're both kind of long-term things that we've actually been doing for many years. One is a line of work that we've come to call integrity by default. We are gradually restricting access to JDK internals, because in order to add new features without drowning in maintenance, we must be able to refactor the JDK's internals at will. Integrity by default is not just about maintainability. It's also about correctness. It gives you more confidence that your program will run correctly. It's about security, and it's about performance, even. Right now, the JVM can't trust that final fields are final, so it can't constant fold them, which is stupid. So integrity by default will fix that. We've been working on this, as I said, for quite a while. We started way back in JDK 9 with modules and encapsulation of most internal APIs. Further work in 16, 17, 21, 23, and 24, and there's more to come. Another thing that helps us deliver more features more quickly is to deprecate and remove old features that just do not serve a useful purpose anymore. There are quite a few of these. We started a long time ago. JEP 117, remove the annotation processing tool, is the first one. The last one, JEP 486 in Java 24, permanently disable the security manager. The security manager and all of its supporting code has its fingers throughout the JDK. It is a horror to maintain, and we are getting rid of it because hardly anybody ever used it. So we've seen some pain points and their solutions. There are many more, of course. I could go on for hours, but I won't. You can learn more about this work and more in the OpenJDK community at openjdk.org. And you can help. The feedback we get from developers who download early access builds, try them out, write little programs to exercise a new feature, run their existing applications on those early access builds, even run in production with them to do some testing. That kind of feedback is priceless. So please join us. You can find early access builds of JDK 25 already on jdk.java.net. You can also find the early access builds for Leiden there, along with the JExtract tool, which you can use with the FFM API. So here's to 30 years of the Java platform, and at least 30 years more. Enjoy the conference. Thank you very much.
Please join me in welcoming Bruno Borges and Mark Heckler to the stage.
All
right, welcome to JavaOne, and thank you for having us. I'm Bruno Borges.
And I'm Mark Heckler.
And we work for Microsoft. But don't worry, Mark's laptop is a Mac, and he will be doing a Java demo. Mark.
And on that note.
Yeah, all right, sounds good. Thank you so much. Funny story, maybe not that funny, but perhaps interesting. As a Java developer, I always wanted to work at Sun Microsystems. But that dream never came true. But I did work for Oracle before joining Microsoft, right here at this office. And it's been 7 years since I left Oracle and have been working at Microsoft, ironically, on a Java team. And together with Mark on developer relations, we have been helping the Java developers use Microsoft product services and tools. Things have shifted a little bit. When I joined Microsoft, the vision was to empower every developer, every person in every organization on the planet to achieve more. That message has been shifting slightly, especially in our developer division at Microsoft, to empower every developer, and especially you, Java developer, to shape the future with AI. Now, things are changing. I mean, I'm sure you're going to notice on Mark's demo that he will not be going on Google or Bing to search for help. He will just be using AI, because that's what lots of developers are doing these days. Not just the use of AI, but technologies like Visual Studio Code, Eclipse, and IntelliJ continue to be the powerhouse of developer productivity. And that allows developers to do that, to achieve more. GitHub Copilot enhances that experience to the next level. I mean, you don't have to Alt-Tab to search on the internet for that answer. You can just ask AI. It could be GitHub Copilot, it could be something else. It doesn't really matter. We do appreciate if you use GitHub Copilot, but if you're using AI to be more productive, that's great. But there is a change in how software is being built, and I personally believe in this thing where the next generation of software will be produced by developers together with AI. Not only that, the software that you're going to write will probably also build software and also run code. So the approach of agentic AI is quite interesting. And we as developers are not only potentially writing software for other developers to consume, we platform developers, tools developers, API developers, but we might as well start to produce code so that AI agents, developers, will consume that. So we got to start thinking, okay, how do I write code? How do I define my API? How do I document my API so that AI agents can consume my code and do what's the right thing to do, hopefully in a deterministic way. The future of applications might as well be this kind of application where it's a combination of human-written code, AI-written code, and AI-controlled flows. So agentic AI development and Gen AI applications might as well be the future. And you are helping shaping that future to some degree, and you might be the consumers or producers or both of that future of applications. Together with AI models, LLM, developer tools, Azure services or cloud services, whatever cloud service that you're using, it's very powerful where the state of application development is today compared to anything that we have had so far. And to that degree, I would like to welcome Mark to do the demo to show some of the components that you see in this chart: GitHub, Visual Studio Code, Java, Spring, Azure services, cloud services, container images, everything that you're probably already doing today. But I'd like for you to experience with Mark how that experience looks like if you are not still doing that. So take over, Mark. Thank you.
Thank you, Bruno. Let's see if we can get this up on screen. Oh, nice. Well, all of us at some point or another have been or will be tasked with creating an intelligent application. And whether that's with creating a new intelligent application or making an existing application perhaps just a little bit more intelligent, we need a starting point. And for new to AI developers or new to this particular challenge, sometimes it becomes a matter of which thread to pull first. So I'm going to walk you through a very simple workflow that I typically use and that many folks use as well. And of course, this is very streamlined based on our time we have today, but I'm sure you can see how to build out from it, and if not, come talk. We're happy to discuss this further. So the first thing to start with is the AI, the LLM, if you will. And a great place to start looking at those and considering those is Azure AI Foundry, as I have here pulled up. Now, I've got this filtered down to just OpenAI models, and as you can see, there are 27 offered at this point in time just with that. But without that filter in place, there are dozens more from a variety of different origins. But I've filtered it down. So at this point, what you can do is start by creating a deployment. Now, I've done that in the interest of time. And as you can see, I have a deployment here for GPT-4o. So you can start working with that, and of course you can start building code to try to run against that and see what happens. But a nice way to get started before you do any of that is to come in here to the chat playground and start evaluating that and see if it gives you exactly what you need. So I'm going to zoom in on this just a little bit for your convenience and say something like, what are the planets in the solar system? And of course, you can have this evaluated. Hopefully it will come back with something that kind of makes sense to us. And of course it does. You know, the LLM is not that crazy. But with the options that you have available, you can choose different LLMs and evaluate them and compare them to see for your particular purpose which one is most fit for purpose. So you can go through that, and once you go through and determine which LLM you want to start with, it's also nice to look at things like, I should actually back up and say, you can fine-tune your models, you can go through different evaluations and score them and compare them, but it's also nice to go and look at your metrics. You can determine what costs will be expected by implementing an LLM within your application in a particular way. Because surprise costs are surprises, and again, no one likes surprises. So this gives you a really good look at what your usage patterns might be. You can extrapolate out from a small case to determine if this fits your particular needs. Once you have determined which LLM you need to use or want to use for your particular circumstances, the next thing you would probably do is start working on an application. Now, I'm going to just spin up a very, very simple application using, again, a very useful workflow here. So I'm going to go to Visual Studio Code and hit the Spring Initializer from here, choose the current version of Spring Boot, and of course, we'll stay with Java. And we'll call this cleverly enough demo. We'll use a jar file. We'll use 21 for now. I need to download my latest JDK. And I'm going to bring in just a couple of dependencies here. Spring Web to get us our web API, and Azure OpenAI. And then I will generate this project. We'll drop this here on the desktop. And then it asks me if I would like to open that. And of course, we would love to open that. And then we open that in VS Code here. And it gives us our nice getting started page. We'll close that out. We don't need that. And then I like to just double check our POM and make sure that our build file has exactly what I would expect it to have. Again, just the fact that we're going to be using an AI through various different parts of our development process and for our end application doesn't mean you can stop thinking, right? We're in this together. So I like to double check this. Everything looks fine in the POM. Our dependencies are fine. But the next thing I want to do, I guess, is really open our application, our main application class file. Very simple, doesn't do anything yet, but here we are. So I'm going to open our, oops, I want to back up there, got a little ahead of myself. I want to open up our GitHub Copilot chat window. And no, I don't want to provide answers to a survey, maybe later. So as you can see, Copilot opens up a window, and if you notice, it brings in the main application class file because I have it open already, and it uses that for context. But I actually want to add just a bit more context here. I want to grab a sample file and use that. If I can grab that here and drag it. Oh, hello, Mac. There we go. And now you can see that I have a couple of files in there for context. The next thing I want to do is just actually do this. So I'm going to copy this to my clipboard on my Mac, a prompt that I've prepared ahead of time, again, in the interest of time, and paste that in. And And without forcing you to read it or reading it to you, it just gives you a basic construct. You're a Java engineer. Here's the setup. I'd like you to create a couple files which allow us to configure our application, and then a couple of endpoints that we can use to access this. And then I'm going to ask GitHub Copilot to generate that code for me. Now, the first option it provides is to create a brand new project, and I don't want that. I want an existing project, the one that I have here. So I'll rerun it without that. And we can see that here is the implementation of the chat controller class and the chat configuration file. Now, I'm going to just take this. We'll assume it's all perfect. And spoiler alert, it's not, because as with everything, there are probably some things we might do differently as we examine this. But I'm going to do that and create a new file, a new class file here. And then I'll go down here to the chat configure class and do the same thing and just add that to our project. Now, that doesn't mean you can stop here, right? We may want to do things a little differently. We may want to change things up. We say, well, you know, let's make this a little more idiomatic. Let's just do that. And we'll create our constructor, do constructor injection. That's good practice. We can change this up, and instead of doing this, we can just return this and get rid of this entirely. And actually, we'll just change this to a chat response. Now, you can do this a number of different ways, right? You can do vibe coding. You can just go back to the AI and just tell it, no, try again. You're really close, but let's do it differently. You can obviously do what I did. You can edit it directly. But it's a great start that accelerates your journey into making those intelligent applications. So I didn't actually show you what this does, because what I asked it to do is create a joke bot. Now, we know that there's a lot of value in that, but that's a starting point, right? So I'm going to, again, because our time is rather short, I'm going to just cut over to my code spaces and show you, well, let's restart that while that's coming up. What we have is Spring Pet Clinic deployed as a series, obviously, of microservices, but we've added here a chat service. And I did, in case anyone's curious, I did leave the joke endpoint in there, but I also added some interesting things that give you the capability to leverage that within the context of our application. So within Pet Clinic, here's our home. Here's our list of owners. We can register an owner. We can check our number of veterinarians or who the veterinarians are. This isn't bad. This is a fairly manageable list. But if we had a large list of customers, we might want to ask which customers are in Monona. And we can find out. Again, in a small number, that's not super helpful, but in a large number, it's very, very helpful, because that way it can go out and find out, determine what customers are in a particular area, geographic area, which comes back just fine, as you would expect it to. If you want to go out and check this out, I've got this deployed again in a code space, and of course, I left in the original tell me a joke, but here's the actual meaty part where we can go in and find the utility, find the useful parts for our Spring Pet Clinic application. I could go so much longer, but I won't. If anyone would like to talk about this later, please see me. With that, back to Bruno.
Thank you so much, Mark. So Java at Microsoft is an interesting thing. Across the Visual Studio family, there are over 50 million developers. That includes Visual Studio Code and Visual Studio. Just Visual Studio Code has over 3 million developers actively working and developing Java applications just like Mark did today. GitHub recently shared the data with us that over the past 12 months, Java is indeed on the top 3 rank of usage. Just GitHub alone, it's 150 million developers coding and writing code and building the future that we all want to see with technology. And together with Azure Services, that is made possible for all of you to shape that future. But that's not done alone, just by Microsoft. That does require a lot of engagement with the community, with you, with our partners, with vendors, with our customers. Our participation in the OpenJDK project is fundamental to that success. Our collaboration with the Eclipse Foundation, with open source projects, that is key for that success. So together with you, we are building that future. We are building the next generation of applications just like Mark did. together with Oracle as well. I mean, if you have an Oracle database and you want to bring that Oracle database next to services that Mark demonstrated, that is also possible through the Microsoft-Oracle partnership. One interesting fact that took us quite a while to come up with and interview lots of internal teams at Microsoft. We shared this data before, but I wanted to reinforce it because it's extremely important so you understand why Microsoft is invested in Java. Microsoft has over 2.5 million JVMs running internally inside the company. These are not customer workloads. This is Azure infrastructure. This is LinkedIn services. These are Minecraft servers. In fact, outside Microsoft, it's big data also, but outside Microsoft, there are over 10 million Minecraft players. Who here has a son or a daughter who plays Minecraft? Okay, who here is still running Java 8? Okay, go talk to your kid, because they are already running on Java 21. Maybe they can show you a little bit of the benefits. If you are on Windows and for some reason you accidentally click on Bing, that's okay. But the reality is that Bing is also powered by Java. All the backend, the indexes, et cetera, use lots of open source projects. Big data is a big thing, and that's not different at Microsoft. We are powered by Apache Spark, Hadoop, Flink, Kafka, Pinot, lots of services, most of them from Apache Foundation. But that's huge, and that's why Microsoft is so invested in Java, so that we can deliver that productivity to our customers, our developers. Speaking of customers, many of them trust Microsoft on delivering that capability of productivity for their businesses and their mission. So if you want to learn more about Microsoft, come watch the sessions, and I hope you have a great JavaOne. Thank you very much.
Bruno, Mark, thank you. Well, this has been fun, hasn't it? Has it? All right, you kind of have to clap if I do that. But before I let you go, we have one more announcement. We spend a lot of time working on websites and material to bring you engaging content to ensure that we're getting the latest material out to you. So we've built sites like dev.java, which is a site for professional developers to find hundreds of tutorials that help you learn all the latest features in an engaging way. We also, well, there's the announcement. We find that our sites have, they're a little intimidating for new developers. And so it's our pleasure to today announce the launch of learn.java, a site that is dedicated for students and teachers and beginners earlier on their journey to learning how to program. Thank you. All right. We got some other great stuff at this conference. It's just getting started. Don't miss the happy hour tonight. And if you really want to get into it, I'm leading a run at 6:30 a.m. tomorrow morning. So come bring your running shoes. We've got the attendee party tomorrow at 7 p.m. So that should be super fun in San Carlos at Devil's Canyon. And on Thursday, we have the community keynote at 8:30 a.m., the unconference at 10 a.m. Bring all of your greatest ideas. It's going to be totally free-flowing and unconference. And then the Architects Fireside Chat will close out the conference from 3 to 4 p.m. Bring your hardest questions for the architects that work on the platform. Of course, I want to take a moment to thank all of the sponsors that really have made Java possible and this conference possible. And finally, I want to thank all of you in the room for coming today, for coming to JavaOne, the almost 1,000 people that have joined us on the stream. All of you make this journey worth it for us. And I want to thank everyone at Oracle for making Java possible. It really is a great time to be a Java developer. Thank you, and enjoy the rest of the conference.
Yeah. Okay. Welcome back, everybody. As an added bonus for everybody who stuck around, we turned on my mic, or rather I turned on my mic this time, so we should have better audio. I'm sorry about that earlier. Yeah, welcome back. I hope I didn't overpromise. I thought it was an excellent keynote. We saw a bunch of interesting stuff. And now we're here to dive a little deeper. I'm here with Dan. Dan, maybe for those people who don't know you, quickly introduce yourselves.
Hi, I'm Dan Heidinga. I am a JVM runtime architect with the Java Platform Group at Oracle. I've been with Oracle for almost 2 years now, but I've got over 15 years of experience doing JVM development and helping to work with Java specifications, especially around the VM and the runtime.
Yeah, and you somewhat recently joined Project Leiden, right?
Yeah, I've been involved in Project Leiden and Project Valhalla and a number of other projects there.
Oh, and maybe I can, maybe I can needle you on Valhalla too, but we're going to stick to Leiden today. So let's first talk maybe about what Leiden is about, and then we'll get into what Leiden has already shipped in 24, and then maybe we can later see a little bit of an outview from there. So yeah, let's talk about Leiden a little bit.
So if you were watching the keynote, you saw Mark talk a bit about this already. Leiden is focused on making Java start up and warm up faster. Java has amazing peak performance, right? We run our applications. We're used to tuning our peak performance, right? We want to get, be able to respond to requests as quickly as we can, take as little time and resources to do it. And Java does a great job of that. And it does that by observing what the application is doing, observing the data, figuring out what methods are called, figuring out what classes are used, the way data flows through the system to find the right paths to optimize and to spend the resources on compiling those. So we observe, then we compile speculatively based on the assumption that those observations are going to continue to hold. So the path that we took last time is likely to be the path we're going to take again. The classes we saw earlier are going to be the same classes. So we observe, we speculate, and then we use that to get the best performance we can. So we speculated, we compiled new code based on that. We've done whatever other optimizations we can. But we always have a fallback path. If that speculation doesn't match anymore, we fall back to something else.
That's like, for example, there's a de-optimization and something like that comes in, right?
Exactly, yes. So Java's really good at this model of observe, speculate with and then get good performance based with fallback. And Leiden says we want to make startup and warm up faster. And startup and warm up tend to be slower in an application because of Java's dynamic nature.
So before we get there, can you quickly explain, just for those who don't know exactly what startup and warm up exactly means? So we get, because to many people I think this sounds synonymous, but you're using it in a very specific way where it isn't actually.
Yeah, and the definitions are fairly fuzzy. So, I'll pick a definition and other people may have slightly different ones. But we tend to think of startup as the time it takes to do the first useful piece of work. So you type Java dash, your application or whatever your command is, and your application starts to execute. But before you execute your first request, there's a whole lot of things that happen in the system. Classes get loaded, the runtime gets initialized, the JIT compilers start up. There's a whole bunch of things that are happening. And that startup is sort of the time to get to that first useful piece of work. And then warm up is from that first useful piece of work all the way through till we hit peak performance.
And useful unit of work, because I recently made that mistake and Mark corrected me. I thought it was like this the first line in my main method basically, but that's not true, because my main method, if it's hello world, then yes, because my first useful unit of work is printing hello world. But if it's a hello world Spring Boot app or whatever Helidon app, then the first useful unit of work includes all the startup of that framework, right? Until
the first request comes in and we've responded to that. That's sort of your startup time.
Right. So it includes potentially a lot of dependencies that have been pulled in.
Okay. And there's work done by the JVM during that time, but there's also work done by your application. Your application is reading configuration files, it's creating loggers and probably more loggers as well. And so it's doing all kinds of class path scanning and all kinds of work to set itself up as well. So startup is not just a VM thing, it's a whole application thing until that first useful response. And then warm up is from there until we hit peak performance. So again, it's a bit of a fuzzy range. You can shift things because things that happen in startup will continue to happen in warm up. You might load new classes as you take different paths. You might continue to compile things. You might continue to profile things. So it's not a clear separation
Yeah. Yeah, and you said like peak performance itself is, there's not like one point when the JVM says, I reached peak, I'm done now.
Yes.
Yeah. Okay, good. So we covered that. So startup and warm-up time. And you said you were going to tell us how Leiden is trying to make those shorter by leaning on Java's dynamic and speculative nature.
Yes. So Java does a great job optimizing speculatively, right? So it observes, it speculates the observation is going to continue to hold, and then it does the optimizations with the fallback. We said, what if we didn't just speculate during an application? What if we were able to speculate across applications? So, and not across two different applications, but across different runs of your application. So you run your application once in a training mode, and then we can use that to record observations that we can use to speculate and then optimize your production runs. So when I say training run, people often say, what do you mean by that?
Yeah.
The best training run is to run your application, right? Like, obviously, your application is going to do the same things it does.
Yeah.
So, if you can train in production and then use that, that's sort of, the best thing you can get.
Yeah.
Otherwise,
sorry to interrupt you, but those, for example, people who do like something like canary deployments, actually in kind of a good situation, right? If they already set up the application in a way where they take the current version and launch it for like a small amount of users, then that would be the perfect training run, basically, right? If then the full rollout would then include this information.
Yes.
Okay, yeah. So that's basically the optimal case, yeah.
Yes.
Yeah.
So, but otherwise, you can take an integration test that executes some common paths through your application and use that as a training run, and you can run that during your build pipeline as well. So you can pre-train or do it at deployment. It really depends on what works best for you.
Yeah.
But the closer the training matches what your application does, the better you get.
I would expect that performance benchmark suites, if people have those, if they are performance sensitive, then often they do have performance benchmarks for their own application. I would guess that those are probably also decent. I mean, I don't mean like micro benchmarks, like full end-to-end benchmarks.
They're good. The big thing you want to avoid with a training run is loading classes that you don't need in your production run. So if your benchmark loads a whole bunch of classes that will never be used in production, that may not be the best training run.
That also excludes unit tests by definition, right? Because like the entire unit testing frameworks and assertion libraries and all of that is in there.
It does. There are probably ways you can configure things to make that more useful.
Yeah.
Because what we've done so far and what we've shipped in JDK 24 optimizes the 3 built-in class loaders: the system loader, the application loader, and the extension loader.
So. Okay. Yeah, right. Let's talk about that though. So what is already before we get there, maybe because we talked about training run, but I know that there's 3 steps, right? Like the training run is the first, that's gathering the data. Let's briefly cover the other 2 steps maybe that's going on.
So the second step, we call it the assembly phase. So in your training run, you record an AOT configuration, and that's where the JVM records the observations it's made of your application. So it records things like which classes you loaded. It records things like which classes were linked together, which constant pool entries were resolved, which Lambda expressions had actually been turned into real objects that we used. And we record that information so that in the assembly phase, where we don't run your application, but we do start a JVM, we can use that to sort of take these classes, to load them, and then to pre-link them together. And out of this, we generate an AOT cache.
Okay.
And then at deployment, you use that AOT cache and you run your application.
Yeah.
So your application runs in training and it runs in deployment, but it doesn't run in the assembly phase. The assembly phase is just a special JVM time for us to sort of put things together in the right.
Okay, just out of curiosity, so I can see that the length of the training run is however long that takes, and then the production run is the time the production run takes. But the assembly phase, do you have is it a matter of seconds even for large application, or would this take longer? Do you have just a ballpark? I know that this is wildly different depending on application, but just generally speaking, what's the time unit that you measure this in?
So now I'm blanking on data.
No worries, it's all good.
It's in the seconds range. It's something that we want to be faster.
Oh, okay.
We've recently had contributions from other groups who've been working with us that have looked at how long the assembly phase takes. Right now, what we're doing in the assembly phase in the Leiden early access builds is more than what we're able to do in JDK 24. So we're doing some code compilation there, And that was a single-threaded process. We were compiling a whole bunch of methods on one thread, and so that was taking longer than we needed it to. And so in the Leiden EA builds, we've recently changed that so that it's a multi-threaded process. We're compiling across multiple threads, and that has significantly sped things up.
Okay, but I'm hearing that, again, there's not a promise, and it's not, and it might definitely, it depends widely, I would assume, on the number of stuff that you're actually doing, which means how large is the application, but also how many of these optimization steps are you taking. But I'm hearing you're measuring this more in seconds than in minutes, for example, just to get a gut feeling for this. Okay, good. So now we have the 3 phases, and we already know that you plan, or that you do some things in 24, and you mentioned that we do more things in this EA build. So let's focus on 24 for now. So what happens, and that's experimental? No, it's final, right?
It's final, yes.
It's already a final feature. Okay, so people can already use that. So what do you do in 24 on this cache?
So in Java 24, we have JEP 483, which is preloading and prelinking classes. So in your training run, we recorded which classes you loaded, and we want to load them in the assembly phase. And we want to not only load them, but we want to link them together. So if you're familiar with CDS, CDS loads classes as you request it. So your application might be talking about a new class it hasn't talked about before, and it says, oh, please go and load this, and CDS has some VM metadata for that class, and it loads it in as you ask for it. But because it happens on a class-by-class basis, those classes are all independent. We can't speculate about the other classes that are going to be loaded before you do the single request. So in 24, with our AOT cache, we are able to speculate that this set of classes is all going to be reloaded as a group. And that means that we can not only load them one at a time with their metadata, but we can actually link them together. So we talk about Java being dynamic. And one of the dynamic features of Java is its symbolic linkage. So when you have a method that has a get static of, or sort of talks about a static field on another class, the bytecode for that is a get static. But that bytecode doesn't link to that field. It links to it by name. It names the class and the field. And so at runtime, the VM runs through that class's metadata, and it finds the actual address or the offset that it's going to use to go and get that field for you.
And that is really important if you do things like separate compilation steps, for example. If this were not the case, then it would be really hard for one jar to depend on another jar, because another jar might make internal changes that would reorder fields or whatever. And if that would be burned into the bytecode, like specific position with an object, then this would not work, right? So this dynamism is something that is not just some fancy academic thing, but we're using it every day.
Every day you take a new jar from another library, or you run Maven update or whatever you end up running. That's using our dynamic linkage. So at runtime, though, the VM has to turn that into real addresses and real offsets that it can use to actually execute. And what we're able to do with the JEP 483 is we're able to do that linkage ahead of time. So rather than doing that symbolic resolution, on first access, we've done it ahead of time, so you don't have to do it again. You just can execute it as though it's a direct reference there. Now, we can do that for field access and method itables, vtables. All these things have special indices that help you optimize there, and we can link those as well. But even more importantly, we can pre-link Lambda expressions. So when you have a Lambda expression in your code, that gets turned into an invoke dynamic in the bytecode. And there's a bunch of work that's done to spin a class file to then go and connect that and load that and whatnot at runtime.
That's a lot of work, right? The initial Lambda setup is quite some work,
And so what we've done is we said we can do that ahead of time. We can do that in our assembly phase for invoke dynamics that we know about. So the string concatenation factory, the Lambda meta factory, and we're looking at other ones as well to see what we can do. We can run those ahead of time, have them pre-linked and preloaded and ready to go.
Yeah, nice. And that covers all the things that are in 24 right now, yeah?
Yes.
Okay, so let's look a little bit down the road. What are other things? Because you mentioned the line EA build, and I think there's more optimizations in there, right?
It does.
Right, so by the way, I hear that the screen share doesn't quite work. Should we take like a 30-second? Maybe you can see whether you're still having it shared in the platform we're using. It's live, so, things happen, but we'll figure it out. I can riff a little bit. I wanted to tell you that these other features that are in the Leiden EA build, you can already try them out. So you can already go to the Project Leiden page and download the early access build. And then you can try this out just as you can try out the feature as it is in 24. And a feature like this that is final, but that is mostly under the hood will still evolve, right? A language feature that is final can't, because that would break stuff, but an internal feature like this could evolve. So that means if you try these things out, the Leiden EA build, but also the just JDK24 regular, and you went through these steps, the JDK enhanced proposal that we're going to point at in a second will contain all the important information you need. And you can try this out, and if you do, please report back. It's very important, like this kind of feedback to what worked. And like, it's nice to hear that things work, and it's always good to get positive feedback. But it's also kind of important when things don't work, right? When you run into an unexpected case or something that you didn't foresee, then that's really helpful.
Yeah, I don't think my screen share is working now.
Okay, then we'll just mention the JEP by name.
To show basically the same performance numbers that Mark showed in the keynote.
Okay. And yeah, right. So, but we can read the numbers, like not the whole number, not all the numbers, but like the average height of these bars here. What number is the JEP though?
The JEP is JEP 483.
483. Okay, so that's the one to check out to see what is available in JDK 24.
Yeah. So JDK 24 sort of lays the foundation for our future optimizations. Because we've brought these classes loaded and linked in as a group, and they all have a stable identity then.
Yeah.
And what that really does for us is it means that we can use that identity to attach other data to.
Mm-hmm.
So in your class, you might have run some method and collected some profiling data for the hottest methods. We can then take that profiling data in the Leiden EA builds and save those profiles and reuse those later as well.
Okay.
So rather than having to start from loaded classes and re-execute and rediscover the profiles, we can say, well, we have a profile already from your training run.
Yeah.
That profile likely holds again. We can use that to drive the compilation that we do afterwards.
But in that scenario, the JIT compilation would still happen in the production run. So it's not, so you're not ahead of time JIT compiling. We're doing
that
as well. Oh, okay.
Yes. So we do the profile collection, and that gives us more options. Once we have the profiles, we can say, okay, we'll compile in your application just like we do now, but sooner.
Yeah.
Or we can say, well, let's do that compilation ahead of time. So we can do the compilation in the assembly phase as well, and we can start you with the precompiled code.
Yeah. Okay.
So we have options. And in particular, because we have the profiles, if the code that you're running no longer matches, maybe you loaded another class, maybe there's a path that your training never took that you start taking all the time, we're not stuck with the code that we compiled ahead of time. We still have that fallback. We can say, wait a minute, our speculations don't match anymore. Let's de-optimize, use the profiles we saved, use the new profiles we've collected, and recompile.
Yeah. So when we talk about, in general, not specific to this performance optimizations, Java is always trying to make the correct case first and then look for optimizations or improvements later, but make sure it's correct. That's the most important part, even if that would be slow or whatever. And then here's something similar here where we say, okay, if your speculative data works out, you're getting a lot of performance for free. But if it doesn't turn out to be correct, you're not bound forever in the slow path.
Yeah.
But you can change over to the fast path. You just take longer to get there.
Yeah.
So in that sense, earlier I said correctness first. You always get correctness. Here you would say you always get good peak performance. But if the profile is right, you get there immediately. And the profile turns out not to be correct, you will still get there. It will just take longer.
Yes.
Okay. Yeah, interesting.
Java's rarely a pick one, lose one. It's a pick both. And so here we're giving you both ahead of time and just in time.
Okay.
And that lets us give you the best possible peak performance.
Yeah.
And get there quicker.
Yeah, that's pretty exciting.
Yeah.
So let's look at some of those numbers. We need to describe them since the audience can't really see them. But I think what I see here is a bunch of bars, and they all top out at 1,000. So that's probably the default scaled performance, launch time or startup time.
We normalized it.
Yeah,
we
normalized
to make sure that the point of this is not to compare the frameworks together.
Yeah.
These are the sort of the getting started applications for each of the major frameworks that we've been looking at.
So we have here Helidon, Micronaut, Quarkus, and Spring Boot as those are like Hello World examples, if I got that correctly. And it doesn't matter how long they take exactly, but the yellow bars are that's the regular time it takes.
That's
normalized.
a JDK 24 build, sort of out of the box, nothing added to it. That's what you get.
Yeah.
Then if you take it and train it with JDK 24, we get the gray bars. So you do a training run, you do an assembly phase, and then you use the AOT cache. We get a 2.5 to almost 3%, 3x.
3x, yeah.
Thank you. Not
Yeah, so we had like, so when this is scaled to 1,000, so we had like 350, so like 35% of remaining time. That's massive, though. It's like a 70% improvement. That's more than I promised people when I talk about this.
That's a large improvement. Now, these are small applications. These are getting started, and they're loading a lot of classes and doing a lot of resolution. So this is sort of a great case for what we can do.
Yeah.
The last set of bars here is Spring Boot's Pet Clinic, so something a little bit larger.
Yeah, a little bit closer maybe to like a small microservice-ish application, backend application, yeah.
And we see, the gray bar is not as big of an improvement because class loading doesn't dominate as much of that.
Makes sense, yeah.
Yep.
So it's like a 40% improvement, which is more in line with what I read from the Japan. Okay, that's where that number comes from, right? Because these are more artificial, the first Hello World ones. This is closer to what you can expect in production.
Yeah. And then what we see, though, is that the green bar there, which is what we get with the Leiden EA, is a larger improvement for the larger application because you're getting into the compiled code sooner.
Right. So the line A bars for the Hello World ones are at around 250 to 320, which is just a little bit better than what JDK24 already does. But yeah, you're right. That improvement is stronger on JDK24, which I guess makes sense, right? There's more stuff that you can probably improve.
Yeah. So with the JDK24, it's the class loading and linking for a Hello World type application, whether it's even with it's a microservices framework or something else with it, it's still a lot of class loading and linking and not a lot of JIT compilation.
Yeah.
And so with the EA build, where we get more profiles and more precompiled code, you get a bigger benefit with a larger application.
Yeah. And does the Leiden EA build, so let's talk about a little bit the future. So I guess the goal is to pull features one by one from the Leiden EA build into JDK mainline. Do you have, I guess you do. How many more ideas do you have beyond what's in the Leiden EA build? I'm sure the Leiden EA build is not the end of the line, right? I'm sure you have more ideas and probably more hypothetical or experimental ones that you're not sure whether they pan out. Can you give us an insight?
Even with what we have in the Leiden EA, there's a lot of work to be done to productize. Right?
Yeah.
We have to find the right tuning. There are different kinds of compiled code that we have. Some of that code says, hey, the first time you talk about a class, we have to initialize it. So we have to do something to make sure that code still has that initialization hook in it. But we don't want that long term. So we have two flavors of code that we can put into the AOT cache. Ones that have these class initialization barriers in it, and ones that are sort of your peak optimization. So we're working on sort of the policies for tuning, when do you switch between those pieces of code? How do we optimize that? So there's a lot of work to go on in those pieces. We're also looking at what else we can do. So one of the goals I have is to be able to take other class loaders and be able to apply the same kinds of optimizations to user class loaders.
Right, we kind of skirted past that. You mentioned that we do the 3 basic class loaders that are part of every JDK run or Java application run. But you're right, like applications can bring their own class loaders along, and you're saying they're fully excluded at the moment from these optimizations?
They are.
Okay.
Right now, when you create a class loader, it's dynamically created at runtime.
So
we don't have the hook to
Yeah.
know which class loader it is, and we don't really have that stable identity yet to know that this class loader is always the same class loader.
Right.
So
Okay.
there's work to be done to say, what have we done here? How do we extend it to your class loaders, to other class loaders? So that's on our list as well. And then there's more sort of speculative things. Everybody always thinks, the more code I can run ahead of time, the better. And we're taking a very cautious approach to that. Not because it's a bad idea, but because it's a very complicated idea and it's very easy to change the meaning of your program.
Yeah. That's like the classic, like you have like a static field that initializes to current time. If you run this ahead of time, suddenly the application thinks it has been running for like days when it has probably just been seconds. Yeah, there's clearly some things that are hard to know whether you can pull them correctly. So I know this is a very speculative question, but what do you think? How low can you get that green bar at some point? This is not a promise. This is just your personal, hopeful guess for the future. So please, people, don't make me regret asking this. Don't take this to the bank. Just like, do you have an idea of how close how low you can get, or a hope, or you just don't want to say? That's fair.
I don't want to say, because I mentioned earlier I've been on Valhalla, and I've been predicting Valhalla will ship soon for years. So
yeah, same. So in the same boat here. But I also learn now. I learned the hard way why Brian is very cautious with these predictions.
Yes, I've been wrong enough years in a row that I'm not going to make predictions ahead of time.
So this is why we don't do it. We don't do it because we're mean. We do it because we're young and eager, and then we get burned, and then we realize, okay, that's a bad idea. Okay, Dan, anything else you want to tell me or the audience before we wrap this up?
That we love feedback. You know, pick up the EA build, pick up JDK 24, start using the command line options. Let us know how it goes.
Yeah, cool. Thank you very much, Dan. And see you around the conference.
All right, thanks.
Okay, thank you to everybody. We're gonna have to switch over a little bit so that Viktor can set up the live coding. I'm gonna do like a mic change. I'm gonna do rearranging the chairs. You're gonna see Billy. Billy, come here. See, there you go. Right, so we're going to do that. And while that's happening in the background, I just want to tell you what else is going on at the JavaOne conference. Well, if you're watching this, you're probably not at the conference, so I'm going to stick to the streams. In California, where we are, it's currently Tuesday morning. On Wednesday afternoon at, I want to guess, 2 p.m. local time, we're going to do another live stream. We're going to talk to, we have conversations like the one we just had with Dan, and we're going to have with Viktor. With a bunch of different people. We're going to look at integrity by default. We're going to look at Java language development in Project Amber. We're going to have Dr. Deprecator here to tell us about all the things he's going to, kick out. He's doing that personally, by the way, so it's all him. So blame him if there's anything ever going wrong. We're going to have Paul Sandos here to dive a little bit deeper into the Panama and Babylon demo that you've seen just now under the keynote. So there's a bunch of stuff that we're going to do on that. And then I'm really looking forward to Thursday morning, again, local time, where we're going to do a stream similar to today. We're going to have a little bit of an opening, which is done by my famous, amazing colleague, Billy. And then we're going to have the community keynote, which is much different from the technical keynote. We're going to have a wide variety of community projects or initiatives that are going on that we're going to discuss. And towards the end of that, we're going to cut back here, and Billy is going to have community guests on. And if you want to learn more about all of that, they are linked in the description down below. Those other streams are already linked, so you can already go there and get notified by YouTube. But also, if you want to get an overview, go to dev.java, and on the landing page, the header, there's like a watch the streams button somewhere. You'll find it. And it contains a page that not only links to all the streams, it also contains the program and what we want to talk about. Okay, now I run out of stuff to talk. How far are we? Okay, Viktor's giving me the thumbs up. Should we just sit down there?
Yeah.
Good. Okay. Cool.
Hey.
Nice to see you. At some point we started fist bumping. Is this like a COVID?
I don't know.
I've seen it on the keynote. Everybody, okay.
I don't know.
Should we do like the real man thing? It's like, there you go. Okay, Viktor. I'm going to scoot over a little bit so I can see you better.
Yeah.
Right. So before we go into the code, what even are we doing here? What are we talking about?
What are we trying to do today?
I mean, it's live coding. You never know, right?
You never know. So we're going to try to use some gatherers and create some gatherers. Just exploring a bit.
Yeah.
Hence the name experiment of the code. So you're familiar with gatherers, or
no? Never heard about them.
Never
just give me just like a brief introduction.
Yeah. So you know Java streams, right? You've used Java streams, and one of the main challenges over the years has been there's been no really good way of how do I add new intermediate operations.
What do you mean there's been no really good way? There's been like,
well, you can sort of emulate in cases, like you can reuse a flat map in some cases, or you can reuse map multi to do. But
okay. I thought you were like the only way that I know to really do is like turning it into an iterator and do like all the things yourself. I thought because that's a terrible way.
Yeah, that's not recommended, right?
Okay, good.
But there has been no extension point where you can add your own intermediate operations. And so gatherers is a way to do that. And there's a single new method on stream called gather, and that takes a gatherer. So if you've used collector before, collector is the API to add your own terminal operations, but gatherers is the API to add your own intermediate operations. So you pass your gatherer into gather, the method on stream, and then you get a stream back, so you can continue working with your stream. And since collectors were terminal operations, and those were, you could implement your own things, but since they're terminal, you don't necessarily have your stream anymore. You have the result of the stream. So you couldn't necessarily stay within the stream. So this allows you to stay within the stream for as long as you want to, and then only when you want to get a result back out, you add a terminal operation.
So the idea is that you do your map at filter and flat map at whatever. But when you need an operation, an intermediate operation that you don't find in the Stream API, I would use a gatherer, right?
Yeah.
Okay, so you're saying it's one interface and one method. So what took you so long?
It's slightly more advanced than that. So there's there's one method on Stream.
Yeah.
There's gatherer, the interface.
Yeah.
There is gatherers, which is some prepackaged
Okay.
gatherers.
Oh, like collectors.
Yeah, exactly.
Yeah.
And then we have something new called downstream, which is an interface that lives within the gatherer interface. And then we have an integrator, which is something new as well.
Okay.
So instead of trying to explain in just using words, let's
do some code.
Try to write some code and explore the problem space.
Yeah.
So in the typical case, you're starting with some sort of source of elements.
Yeah.
So let's define a source of elements. So let's use a list here.
Yeah.
Let's use 1, 2, 3. That's not super helpful, but okay. So now we have this very rudimentary source of information. And we want to do something with that source of information. So we create a stream out of that. So source, stream, and now we want to use our gatherer. So here's the gather operation. And now the question becomes, okay, so where do we get a gatherer from? So let's say that we just want to explore, how do I create my own thing? And the simplest thing in that case is probably to just pass information through. Let's just do the scaffolding and just pass elements through, and then we can start exploring.
So it's like a no-op, yeah?
Exactly. Well, not no-op in the sense of, hey, it doesn't do anything, but it still passes things through. But
good point, so transparent, maybe.
Yeah, it's like map identity. If you think it just applies the identity function to the stream. So we do use a factory method on gatherer. And there are several different permutations of this factory, but we're going to use the simplest form. And that allows you to pass in a lambda, because it takes an integrator, but integrator is a single abstract method interface.
Yeah.
So now we can, so we can pass a lambda to this. And what signature is that? So we have a state.
Can we scroll a bit? So in case you see the camera down here, so
let's
make sure
add,
that they see all the code.
Add some more lines here.
Yeah, exactly.
So
gatherer, so integrator, set is a function interface. So I'm immediately thinking input parameters, output. So input is apparently some state. And then what else? What are the other things?
Exactly. So for each element of the stream, we're going to get called here. And we're going to get called with the state, which, so gatherers are optionally stateful. And since we aren't specifying any specific type of state, that's going to be void. So we're going to be passed a void every time.
Okay,
so
we
it's
can't use this.
stateless,
We can't really use the states. Can we use the underscore there, right? I mean, you're probably going there anyway.
We can. I was just trying to be clear about what we're seeing here.
I was trying to be clever, but okay, keep going, be clean.
There's probably going to be a few sort of Klang-isms in my code here that I'm probably going to have to explain. But so we get the next element, or the element that we're going to work with, and then we get this magical thing called a downstream. So that represents a handle to the thing that is after this gather operation in the stream pipeline.
So when I write the pipeline, it's like it's the next operation. So in this stream pipeline, there is no next operation yet, but we need something anyway. Yeah.
We're going to add that.
Oh, you got the fancy
Yeah, I have some ligatures enabled here. So
sorry, for those not aware, this is just a regular dash sign that's intelligent.
This is just
in a nice way.
This is just me liking typography.
We should do a typography stream.
So what we wanted to do here, right, was that we wanted to pass the current element downstream and not do anything else with it. So we call a method on downstream called push. So we push the element downstream. That's all. That's it.
And that's the transparency there, right? It doesn't do anything.
Exactly. It just
takes
pushes the element downstream, and then let's say we want to create a list out of this. So essentially what we want to make sure is here, we pass in a list of integers, and we expect to get the exact same or an equal list out, right? So we get some bar result here. All right. So now we have a source and a result. So let's do the the print out thing here. So let's print out the result. So what are we expecting here?
1, 2, 3, yeah?
We're expecting 1, 2, 3. All right, and we get a list of 1, 2, 3. So success, right?
Yeah.
Success. That's great. All right. So that is the simplest case.
Mm-hmm.
And that's arguably not better than just calling map with an identity.
Yeah,
function,
that's
right?
like it's
right. So this is sort of the simplest thing that we can
We see the scaffolding, but it doesn't do anything helpful.
Exactly. But what we could do here is, so what does push return? So push returns a Boolean.
Okay.
So, and that Boolean indicates whether we want more elements or not. So whether we want the next element.
So in case, like, because the downstream could just not, so if you do like a find first, then the downstream only wants like the one element.
Exactly. So let's say we want to push the element downstream, and then we want to say we don't want any more elements. So the first element we get, we push it downstream, and then we return and say, hey, we don't want any more elements.
Oh, so now you're turning this into basically a short-circuiting intermediate operation.
Exactly.
Also, this one now says, okay, to give me, so this one signals independent of what downstream wants.
Yeah.
Okay. Oh, okay.
So right, it doesn't matter if the downstream wanted the element or not. I don't want any more elements.
Okay.
So realistically here, we're going to want to see a single element list containing the number 1.
Yeah.
Right. That is what we're expecting here. So let's see what happens. We get a single element. So we could essentially decide that we didn't want any more elements at this point. So now we can both transform elements because we could.
That's really cool because that means that you can have intermediate operations that like search for specific things, and when they're done, they signal
specific conditions.
Something like take while basically, which does something like this, right? Take while decides I'm done now, regardless of what downstream wants.
Yeah, or you're doing something special where you're looking for the max element in a list of numbers, and you know what the maximum possible representable number is.
All right.
You could short circuit immediately when you see that because you don't know there's not going to be any other numbers bigger than that. So what we can do here is we can start to add all kinds of things that we would like to do, right? We are working with numbers here, so we could transform the number. So in this case, we would like to see the number 2 being emitted because we get 1, we add 1, and then we say that we don't want any more elements.
Yeah. Oh, this turns the gatherer from a gatherer that works on all types into one that now only works on a specific number type, right?
Exactly. Yeah. So the interesting thing here is that we are defining sort of inline here that we have a gatherer, but in a lot of cases you might actually want to abstract over something. So you might want to, if you want to create your own intermediate operation that is sort of fancy, but you still want to have it use different types of elements, you're going to need to be able to specify what types of elements those are.
I have to come clean. I lied to you earlier. I've actually already used the API, and that's something that was really, I found really enjoyable, that you can really, really easily end up. This is basically just an extract away from having a reusable building block that you can then use in every other stream. And you know, of course, these intermediate operations are not that common as the ones that are already there. That's why we're not there. But it's so nice to build up a little library of just reusable chunks, and I found that this is really like it's really amenable to that. Like I've actually never done this, to just have the inline gatherer.
No, I think there's a really nice story for you're exploring a bit, you're seeing what you need, and then once you've found what you need, you can decide, okay, should I leave it inline or should I extract it into its own method, or should it be its own class? And implement the interface gatherer yourself. So you have multiple ways of deciding where the appropriate scope for this thing is. So now we have this thing. The funny thing here is that we haven't said anything about parallelization, right?
Oh yeah, true.
We haven't said anything, and this is just a list and a stream, so this is just a sequential stream. But the funny thing here is that since it's a stateless stream, what would we expect to happen here? Right?
I don't know, man.
Yeah. Well,
it doesn't. So it picks the first element, but in a parallel situation, I don't know what the first element.
First of what?
Yeah, exactly. That's what I'm saying. That's what I'm saying. So the return false means it only processes 1.
Exactly.
Which one is now unclear because that depends on which thread does it first. But it's just 3 elements. Do we get splitting behavior here? I'm guessing 2. Yes.
Yeah. So interestingly, I have a presentation on this afternoon.
Okay.
So if anybody who's watching is interested in learning how this actually works, because this is actually parallelizing this, but still always generates the correct result as you expect, because you don't want, or most often you don't want your thing to behave differently sequentially than parallel,
yeah,
right?
definitely. I mean, there's some things where like find any, find first, where the actual contract is like, it doesn't matter to me.
Yeah.
Like if I do find any, I'm intentionally saying I don't care.
Exactly.
But in most of these situations, that's also true. Like the gatherers that I wrote, the logic was always inherently sequential. Like I didn't even come up with a use case so far which would even make sense in a parallel world. By the way, I just learned that we lost your screen share. Can you? No, we're good. We're good to go.
We're good again?
Yeah, it was Billy's mistake.
Okay, misclick.
No, it's a mistake.
All right, so what we can do here, so this is
for the audience at home, like Billy's fine with this. We just keep like this. I'm not being a bad colleague. I'm just
So what we can do here now is we've defined a very simple, stateless, but it's still short-circuiting and it's still parallelizable. But what we can do now is we can try to use something which is stateful. And let's start with reusing something that already exists so that we can get a sense for what statefulness really means. So we have gatherers. So that's our sort of pre-baked one. And let's do window fixed of 2. And let me just explain that. So let's say that you have a stream, and this wasn't necessarily possible before because you couldn't necessarily keep track of what you had seen before. So what window fixed does is it takes a stream and it divides it into lists of the size that you have specified. And of course, if it doesn't pack neatly into that size at the end, you might get a shorter list at the end. So in this case, we want windows of size 2, but we only have 3 elements here, right? So we're expecting to get what? We're expecting to get one full window and then an extra window at the end.
I actually wrote a blog post years ago. I wanted that behavior, specifically that intermediate operation that does this. And it falls apart. You can build something like this if you're willing to build state and everything, but it falls apart without gatherers because like the last group will not be finished. What you do is you build up a list, and when you hit like the number, you emit it.
But you don't get any end of stream signals.
Right, so I found another way around, which is really ugly, which is you emit on the first element, you emit a mutable list, and then you backfill it while the next elements come in. That is really horrible.
Well, what happens with dot parallel on that?
Yeah, that's I didn't even try. But that's how desperate I was. But then I coded up and it kind of works, but also clearly terrible because you have like there was also one I can't cover it now. One specific thing where actually even without parallelism would go wrong. I think it was on short-circuiting operations then, because then would suddenly if you don't process more elements upstream, then I cannot fill the mutable list. It's a train wreck. So this is really, really nice. So the fact that this can emit a 3, as ridiculously trivial as it sounds, is really the game changer, whereas this you could definitely not build with like a fancy map or whatever that I tried before.
And what you can do here is that if you don't want to have an unevenly sized list at the end, you can always run a filter afterwards and say, I just keep things that have the size that I'm looking for. So in this case, 2. So should we try to make an attempt to create something sort of like window fixed?
Okay, so we would plan to stream until about now, but we don't really have anything coming up right after. So as long as the audience is willing to like stay along, let's just do it, and David and Billy will just kick us off stage when it's okay. So let's try to implement window fixed.
Okay,
but only for the sequential case. Yes, please.
So
where's the fun in that?
So what about instead of implementing something that is already there, because that's not super fun, but let's say that you wanted to create a window that groups things together according to some predicate. So let's say that we want to it's artificial in this case, right? We don't necessarily have a use case, but let's say that we want to stream over characters or something, and we want to group all the lowercase characters into one window, and then if there's some other, it's sort of like a parsing style thing.
Okay, let's do that.
So let's just start with, okay, so what kind of specification are we working with? So we're going to create a method that returns a gatherer, because we're working with some predicate, and that predicate could change, right? So you might want to look for lowercase numbers, some other one might look for something else. So we need to be able to make that a parameter. So let's make a public static thing that returns a gatherer. Okay, so what's the type of a gatherer? Because it has some type parameters.
I assume like input and output type must probably be present. And
exactly.
That's it?
Strictly, yes. There is another type, which represents the type of the state. But typically, you don't want to expose what your internal state representation is, so you typically just leave it as a wildcard.
Yeah, like the collectors, right? They do the same thing. Okay.
So in this case, we want to have something that takes t's as input, and it has some state that we don't necessarily need to tell anybody what it is.
Yeah.
And then it's going to produce lists of t.
Yeah.
So the windows, right? So we call this window by. Let's create a new line for the parameter. So we have a predicate of something of t, right?
I'm just smiling because you can't bring yourself to.
I'm sorry.
Just not doing the wildcards, because demos like this, I just ignore wildcards like this. Keep going, it's fine.
I've been doing it too many times. So that's
I appreciate, by the way. I'm pretty sure this will take you like all of 30 seconds if you wouldn't try to tell me what you're doing.
All right.
So taking the predicate, yeah.
So now we have a signature. We're going to produce a gatherer that takes some sort of t and produces lists of t's.
Yeah.
So, all right. So what do we need? We need to keep track of state, right? Because if we're going to bunch things together into windows, we're going to need to remember what we saw before.
Yeah.
So some sort of state.
Also, maybe just to know where we're heading with this, if I understand this correctly, we have like a stream of unknown of elements.
Yeah.
But the downstream will definitely contain just exactly two lists, right? Because it's a predicate, it will contain the trues in one list and the false in the other list. Right?
No, it's not a partition by.
Oh.
So if
you want to run.
Yes. So let's say, just to create an example here.
Yeah.
So let's say we put in a bit of an ad hoc spec here. So let's say that we get A and then B and then C and then a capital A and a capital B and a lowercase c. We would like to see as output a list of A, B, and C, and then A, and then B, and then C.
Wait, why are A and B not in the same one?
Because let's say that the predicate here is, as we talked about before, is lowercase.
That's how it feels to be this. Okay. On stream two. Okay, I get it. Okay, so these are false, and so this.
So any consecutive lowercase character in this case would get bunched into one window.
Yeah.
And then when we see something which is not a lowercase, that would essentially emit the current window and then create a new one element window saying that, okay, this is not. So this is sort of like a grouping exercise.
Okay. Victor's screen is stuck now. Can we do something? Yeah, and it's back good. So apparently there's the occasional issue with the screen share.
It's probably Wi-Fi.
Yeah, it's playing Wi-Fi. Yeah. So you can also see, by the way, like the way we're discussing through this, the exact use case here is extremely arbitrary, right? Like it really depends on the use case that the person has. Right? Maybe they want A and B to be in the same group. Maybe they don't.
Exactly.
And so the idea here is not to provide a gazillion more intermediate operations in the Stream API for all of this. For all of these uncountable combinations, but to say, no, look, you get your own extension point, and you can go crazy with all the specific use cases that you need, without us having to say, well, is this general enough to make it into the API? Because a map and a filter is like the cornerstone of this API. Clearly, it must be in there, but everything from there, a flat map also, but everything from there is basically up for discussion. How important is it? What do you need? And so clearly, the JDK has to draw a line somewhere.
Yes, yeah, absolutely. I mean, some intermediate operations might be super important and very frequently used in a specific domain.
Yeah.
But how do you draw the line and say that, okay, so it's significant enough so that everybody should have to scroll through it when you get a dot completion list? It could be thousands of methods, right? So let's see. We need to keep track of something which is sequenced here. So let's use an array list. I like array lists. And it's going to contain some t's here, right? Let's see if we can. No, it doesn't work.
No, that I don't know.
Yeah, it does. It does. It does. Why doesn't it want to?
I think so my experience with this is until like you have the full number of parameters there.
All right. Let's work with some partial compilation tricks.
Right. So what you're doing here is you're telling the API how to create a new state.
Yes. So I'm saying that I give you a supplier of this state, which is whenever you call the supplier, you're going to get a new array list.
Yeah.
So we're going to work with this array list for our state. And then I need to pass it the integrator that we talked about before. So in this case, it will be our list, the state, and then we get an element, and then we get a downstream, right?
Yep.
And we're going to have to do something there, right?
Yeah.
But
can we scroll up a bit?
Yeah, let's scroll up. And we also know that we're going to have to react to end of stream, because in this case, the last letter here is a lowercase c. So if there was a next element, right, that will go into that. So we're going to have to react to end of stream to flush out any predicate matching things that we have currently batched up. So the end of stream hook is similar to the collector end of stream hook, the finisher. And that gives us our list, and it also gives us a downstream handle.
All right. There's no element because, with the end of stream, there are no elements.
Exactly.
Okay.
All right. So now, though, you see the of factory is complaining here.
Yeah.
And it says to us that you need to provide a combiner function. And this operation here, the window by operation, is inherently sequential, right? Because we don't know that it's something that follows something else unless there's a given order.
Yeah, yeah.
So we can't parallelize this in the same way that we would be able to parallelize something that had a combiner.
So the combiner is used for parallelization.
Exactly.
Or rather, I guess, because of the name, when you are done parallelizing and you're merging stuff together, right?
When you've forked everything and you've processed everything, now you need to combine all of these forks into one truth. So we can't do that, and we need the sequential guarantees. So we say that we're sequential.
Yeah.
And that allows us to run this gatherer sequentially in a parallel stream. So it's not like you're opting out of being able to use your gatherer in parallel streams. You're just saying that when you run this gatherer, this must run sequentially.
So the rest of the pipeline is still running parallel potentially? I mean,
but depending on the stream implementation.
Yeah.
All right. So let's see if we can make this work. Can we make this work?
Can we make this work? Is it? Okay.
The screen is gone again. Okay, so I guess people can hear us. So let's
let's talk through it. So you have in mind the new state, and then the integrator. And now what do? We're basically hoping that this comes back soon.
Yeah.
So okay, so right. So what the integrator got the list, the element, and the downstream. And now my understanding is we test the predicate and we stuff things into the list, or we emit the element.
Exactly. So first we need to check the predicate if the next element matches. And if it doesn't match, we know that if we already have something batched up, we should be pushing it downstream, right?
Yeah.
So we need to convert our current list of things. So if our list is empty, or if it isn't empty, right? If we have something to push, then clearly we need to push it downstream. So we need to do downstream push, and let's convert it to a immutable list.
Yeah, I think that's really good advice. So in general, when you work with stream pipelines, don't work on mutable state. Like you don't want a map function, for example, that just changes things while it's working. You want to map from one result to the other. So I would always recommend to do copies like this, or definitely.
Exactly.
Don't pass like an array.
Let's see if we can make this.
I think like this method still doesn't return. I think that's throwing it off, at least in my experience.
No, it's
better. Okay, yes, I'll shut up.
Incrementally looking better.
Yes.
All right. So if we don't match the predicate and we have something that we've already batched up in a window, we're going to push that window downstream. All right.
Yes.
And if it isn't, or if it is empty, then there's nothing to push that we've already batched up.
Wait, but don't we need to do more here?
We need to do more here, right? Yeah. We need to clear out the list, right? We don't want to send the same elements twice.
But also we need to emit the element itself, no?
Yes.
Ah, okay.
Yes. That is true, but we need to do that no matter what, no matter if the predicate matched or not, right?
No, I think it's not. No, I think it's not. Is it?
Yeah, it is.
No, wait, it's a predicate. Okay, I'll let you go, and I'll trust you on this, and maybe I can complain later if I think the logic is wrong.
So what we need to do, no matter what, is to emit something.
Yep.
Right. So if it if it matched the predicate, we need to batch it.
Yes.
Right. All right. So let's do that. So list add element. All right. So that is, we need to close out the window. We need to push it if there is anything. And then in this case, and that's what I meant, we need to push the element downstream.
Yeah.
Right. So we need to do a downstream push of the element.
Oh, that's why I didn't want to put it in there. Get it now. Yeah.
Yeah.
Oh, list off though.
Yeah. We need to do a small one element immutable list. All right. So but this is just, we're just exploring.
Yeah.
We're trying to see if we get the requirements right. But then we also need to return whether we want more elements, right?
Yes. Yeah.
And in the typical case, what you want to do is you want to decide, is this operation a short-circuiting operation or not? This is not a short-circuiting operation. However, when we push something downstream, the downstream could tell us that the downstream doesn't want any more more information yet. But just for now, just to make a small test, before we propagate that signal, let's just say that we always return true. This is just for now.
Can you write above that line a to-do that says something like fix later?
Fix me, propagate, push, return.
I'm afraid we need to scroll a bit probably.
Yeah, all right. So this is not going to make it into any production environment. That's for sure.
Wait, this is not the OpenJDK code?
All right. The simplest thing here is the finisher, right? Because the finisher essentially says
downstream push list copy off, I would guess.
Well, first we can do like list is empty, right? We don't need to push anything.
Good point.
And then we can also test something interesting here, because if the downstream didn't want any more elements because there was a short circuit, it will say that it was rejecting something. So if it isn't rejecting and we have information, then we can push it downstream. So downstream push list.
I have a question. Like if I don't include these checks, well, this empty check I need. If I don't include that, I push elements I don't want. If I don't include the is rejecting test, I would guess I would still get correct results, just I do unnecessary work.
Exactly. I mean, the thing here is that let's say we don't check is rejecting here, just for the sake of the argument, we are still going to create that list copy of. And that might be wasteful in the case where there's nobody who's really willing to accept the copied list.
And then so the downstream just discard it. So this signal, the signal is needed for optimization, for performance, but it's not needed for correctness. It's interesting. Okay.
Yeah. So let's have a look and see if this does what we think it does. I think that's a good question to have right now. So let's say we do window by, and we
even not maybe.
No. Let's take the example that we had down here.
Okay.
Because then we know what we are expecting anyway, right? So these are the letters that we're going to work with. So these are characters now, and we have to check and see if the character is lowercase, right?
Yeah.
So now we should be getting the thing we expected down here.
Yeah, that's for fun. Let's format this in a way that would probably look like a user code, right? You usually put together and then the window by like on the same line, just so people get a better impression, because this now looks a little more complicated than it really is, right?
Let's we can simplify
this is what your Streamline probably looks like, right?
Yeah.
You have maps and filters and whatever else around.
Clean it up a bit.
Right. So I'm just thinking, because so people get an impression of what it looks like, because if you got done the work to put the, like in this case, like a static window by function somewhere, then the pipeline itself looks really natural. You will see, depending on what you're doing, you will regather a lot, which you have to like glance past, but I think pretty quickly people will, like the gather is just like, usually the stream operation tells you which building block am I using. With gather, you have to look like a little bit further to the right and read the name for that building block. And my experience is we adapt pretty quickly to this, and so you can really easily follow. Okay.
Yes. All right. So moment of truth.
Moment of truth. If this works, we're done. If it doesn't, we're also done.
Let's see.
Okay, I hear there's no screen share, but we'll see. We'll just tell people that it worked. It did work.
It did work. It
okay.
did work.
We'll just wait for the screen share to come back so people can see the output. Okay, good. So
so next week we'll do the fix me.
Yes.
Is that...
No. We check this in.
Yeah.
We open a Jira, and then we go on holiday. Okay. So this is now final. So I cannot tell people to test this and give feedback. I can people to use this in prod and be happy.
Well, you can always encourage people to give feedback.
Okay, that's what I was asking for. So it still makes sense to come to you with ideas on this. Well, or not to you necessarily personally, but which OpenJDK mailing list is in charge of this?
This is Corelips. Yeah.
Corelips, okay.
And I mean, it's really hard for us to know what use cases are out there, right?
Yeah.
And there might be new use cases that haven't even been thought of yet. So try things out.
Yeah.
Tell us what worked, what seemed surprising, or if there are any things that that is missing, or any.
And also the reusability of these gatherers already sprung up a few open source projects. I know one by name, which is Gatherers for J, but I think there are one or two more already that are doing this, right? That they were mentioned in the past, mentioned just now, which is come up with things you could potentially do, and it's really fun. Like one of them opened an issue, and I was like, "Hey, I can implement this." And the maintainer was like, "No, I wanna," because it's fun. Like working with streams is fun in general, I feel, and working through gatherers is fun, and then seeing the emergence of these. I mean, this what you're showing right now is not exactly like you look at that and be like, "Oh yeah, no, sure, that makes sense naturally." But once you get used to the API, it actually does. Like you have this idea, okay, I'm going to get my state, I'm going to get my element, I'm going to get the downstream, I'm going to do the things I need to do, and once you get used to it, it's pretty straightforward. But more importantly, I don't need to know any of this. I'm just going to look at the Java doc of what window by does, and there you go. And then I can just really use this in a really nice way. So I really appreciate this addition. I've been wanting more stream features for a while. This is the first major change, I think, in quite a while. Map multi was like a baby step in that direction. Can we deprecate that now? I'm going to ask not to deprecate it tomorrow. Okay, I think that's it, right?
Yeah, thank you.
Thank you, Viktor, for being here. Thank you, everybody, for watching. I had a blast. I hope to see you again, as I said, tomorrow at 2 p.m. Pacific Daylight Time, PS, whatever, California time right now. And yeah, I guess that's it. I don't know what else to say. Have a good one. See you. I will awkwardly wave until David puts me off stream.